Tonight, let us go somewhere warm. Picture a small island far out in a wide, dark ocean on a night with no wind at all. The sea moves against the black rocks in long, slow breaths, in and out, never hurried. The air smells of salt and wet stone and something faintly mineral, like a struck match held a long way off. Above you the sky is thick with stars, more stars than you would ever bother to count, and low on the horizon where the land rises into a shape too gentle to be called a peak, there is a glow. It is not fire the way a lamp is fire. It is softer than that, and older. A slow orange breathing against the underside of a cloud, brightening a little, fading a little, brightening again, as though something enormous and unbothered were turning over in its sleep. Every few minutes a small bright thread runs down the dark slope and cools to nothing, and the glow settles back into its patient rhythm. If you were to lie down on the warm ground and put your palm flat against it, you would feel the heat coming up through the rock. Not the heat the sun leaves behind at the end of a hot day. This heat comes from underneath. It has been traveling upward for a very long time through miles of stone, and it will still be traveling upward long after tonight has been forgotten. That warmth under your hand is the subject of this whole quiet evening. It is the oldest engine on the planet, and it built almost everything you have ever stood on. Now, before we go any further, settle yourself properly. Let the lamp go dim, or let it go out altogether. Feel where your body meets the bed and let it meet it a little more completely. Let your shoulders come down from wherever they have been holding themselves all day, one quiet inch and then another. Unclench your jaw. Let your hands go soft and heavy. There is nothing in this evening that requires you to be alert and nothing you are meant to remember in the morning. If you enjoy what I make here, and only if you truly do, a like or a subscribe helps this channel find other people who cannot sleep. And if you feel like it, leave your town and your local time down in the comments. It is a strange and lovely thing to scroll through and find someone lying awake 9 time zones away, listening to the same soft voice you are listening to now. It helps other sleepless people find their way here. Tonight I am going to tell you 100 small facts about volcanoes. Fire mountains, if you prefer the older name for them. Ash, lava, hot springs, black beaches, islands born in a single summer, skies turned strange for a year, and the slow patient heat that made the air you are breathing. You do not have to hold on to any of it. Let the facts pass over you like weather. If you fall asleep at the 11th one, that is not a failure. That is the whole point. I will keep talking gently in the dark either way, right through to the end. Let us begin one layer further back than volcanoes, because before there could be a volcano there had to be a world with something hot inside it. 4.5 billion years ago, there was no Earth at all. There was a flat spinning disk of dust and gas going slowly around a young star. And in that disk, the dust began to stick to itself. Grains found grains, pebbles found pebbles, boulders found boulders, and then, over an unimaginably patient stretch of time, boulders found each other hard enough to make mountains, and mountains found each other hard enough to make a world. Every one of those collisions turned motion into heat. A falling rock carries energy, and when it stops falling, that energy has to go somewhere, so it goes into warmth. The young Earth was assembled out of 100 million small arrivals, and it came out of that assembly glowing, soft, and molten nearly to its center. Then it was struck by something roughly the size of Mars, which is the sort of sentence that sounds like an exaggeration and is not. That collision melted the outside of the planet all over again and threw a great ring of debris into orbit, and out of that debris the moon gathered itself together. So the moon in your window and the heat beneath that island are, in a manner of speaking, siblings. After that, the planet did what any hot thing does. It began to cool. But it is very large, and large things cool slowly, and there was a second source of warmth that no one suspected for most of human history. Scattered through the rock in tiny quantities are atoms that are quietly unstable, and as they come apart, they give off a little heat, not much, from any single atom. But there are a great many atoms in a planet, and they have been at it without a break since the beginning. So the Earth kept its heat. It still has most of it. Underneath the thin, cool skin that we live on and build on and argue over the ownership of, there is a body of rock hotter than a furnace, moving so slowly that a human lifetime cannot see it move at all. A volcano, in the end, is simply a place where that inside becomes briefly visible. That is all any of them are. Not monsters, not punishments, not the wrath of anything. Just a small, honest window in the floor of the world, opened for a while and then closed again. Though it took us a remarkably long time to arrive at that plain description. For most of human history, the explanation was a workshop. A smith, a forge, a god at work below the ground, hammering out armor or thunderbolts, and the smoke of his labor rising through a hole in the roof of his house. That was the Roman version, and it was not a foolish guess. It fitted the evidence available to anyone standing on a beach in Sicily watching sparks go up into the dark. There was heat, there was a rhythmic sound, there was slag, and there was a chimney. Any reasonable person would have concluded that somebody was making something. Other cultures reached for other pictures. Some told of a spirit of the mountain with a temper and a long memory who could be reasoned with and who noticed how she was treated. Some told of a great creature turning over beneath the island. Some kept careful, entirely practical records of which slopes had burned in which generation, which is a form of science whether or not anybody called it that. The change came slowly, and mostly through people who were willing to walk up and look. In the 1700s, a handful of travelers began climbing active mountains on purpose, taking measurements, drawing sections, and noticing that the layers in a cliff face on one side of a volcano matched the layers on the other, which could only mean the mountain had built itself in stages out of its own output. Then somebody realized that certain dark rocks in northern France, far from any known volcano, were unmistakably lava, and that the round hills they sat on were the worn stumps of vents that had gone quiet before anyone was there to see them. That was the moment the subject grew up. Volcanoes were not an occasional disturbance in an otherwise finished world. They were an ordinary and continuous process that had been running everywhere all along and had shaped the whole surface, including the calm green places where nothing had happened for 1,000,000 years. Everything since has been detail, instruments, and patience. Let us look through 100 of those windows tonight. 1. A volcano is not a mountain. That is the first small correction, and it changes how everything else looks. A volcano is an opening. It is a hole in the crust where melted rock has found a route to the surface, and the mountain that we photograph and put on postcards is simply the pile of material thrown out of that hole and stayed where it landed. Think of an anthill. Nobody would say that the little cone of sand is the ant colony. The colony is the tunnel and the chambers and the traffic underneath. The cone is only the tailings, the crumbs left at the doorway. A volcanic mountain is exactly the same idea, built on a scale that takes many thousands of years and reaches a mile or two into the sky, which means a volcano can exist without any mountain at all. There are volcanoes that are simply cracks in a plain, long, gentle fissures that pour out rock and leave the land almost as flat as they found it. There are others that are holes in the seabed with nothing above them but water. There are volcanoes whose mountains have already collapsed back into the ground, leaving a wide, shallow bowl where a peak used to stand. The mountain, when there is one, is the receipt. It is evidence of past activity, kept in stone, stacked layer on layer, oldest at the bottom and youngest at the top, exactly as a book of the place would be written if the place could write. 2. Magma and lava are the same substance. They differ only in address. While the melted rock is still underground, it is called magma. The moment it reaches open air, it is called lava. Nothing about it changes in that instant except its location and, immediately afterward, its behavior, because at the surface all the gas dissolved inside it is suddenly free to leave. That distinction sounds like a small piece of vocabulary housekeeping, and it is, but it points at something real. Underground, the rock is under enormous pressure, and pressure keeps gas politely dissolved. Above ground, the pressure vanishes, and the gas comes rushing out of solution, and the same fluid that was creeping upward in silence starts to froth and fountain and hiss. You have watched this happen on a kitchen table. A bottle of fizzy water, sitting closed, is perfectly calm, and the gas is in there the whole time, invisible, held down by pressure. Open the cap and the drink foams up the neck. The liquid did not change. Its circumstances changed. Magma also carries crystals and bubbles and sometimes broken fragments of whatever rock it has been traveling through, so it is less like a pure liquid and more like a thick soup with things floating in it. Geologists sometimes call it a melt, which is a nicely modest word for something that can build an island. 3. Rock does not melt simply because it gets hot. That is the second correction, and it surprises almost everyone. Down beneath your feet, most of the rock is hot enough to melt in theory, and stays solid anyway, because it is also under tremendous pressure, and pressure squeezes the atoms so tightly together that they cannot take up the extra elbow room that melting requires. Heat says yes. Pressure says no. Pressure usually wins. So melted rock is made in 3 ways, and only one of them is what you would guess. The first is by adding heat, which happens where a plume of especially hot material rises from far below and warms the rock above it. That is the obvious route and the least common of the 3. The second is by taking pressure away. If a body of hot rock rises, even without getting any hotter, the weight on top of it decreases, and at some point the squeeze relaxes enough that melting can finally begin. This is called decompression melting, and it makes most of the melt on this planet. The third is by adding water. Water gets into the mix at the edges of the seabed, and water lowers the temperature at which rock melts. Exactly as salt lowers the freezing point of ice on a winter road. Add a little water to hot, dry rock, and it will begin to melt at temperatures where it would otherwise have stayed stubbornly solid for another 1,000,000 years. 4. Once rock melts, it goes up. It has no choice. Melted rock is less dense than the solid rock around it, typically by a few %. And in a field of gravity, anything less dense than its surroundings will try to rise. It is the same principle that lifts a cork through water and a hot air balloon through cold air, applied to something with the consistency of very thick honey and the temperature of a foundry. The rising is not quick. Magma can spend thousands of years working its way upward through the crust, pausing wherever it finds a layer it cannot easily push through, spreading sideways, cooling a little, gathering itself, moving again. Sometimes it never arrives. Most magma never reaches the surface at all. It stalls somewhere within the crust, cools slowly over ages, grows large, well-formed crystals as it cools, and hardens into granite. That granite is the same journey as a volcano, only interrupted. The pale speckled stone on a kitchen counter or the gray slabs of a cathedral step is failed lava. It set out for the sky and stopped a few miles short, and then the land above it wore away across some 40 million years until it stood in daylight after all. So there are two endings to the story of every batch of melted rock. It either becomes a volcano quickly and visibly, or it becomes a mountain range slowly and in secret. The second ending is far more common. 5. At this moment, somewhere on the surface of this planet, roughly 20 volcanoes are erupting, not building toward it, not threatening it, erupting right now, tonight, while you lie in the dark. Some are producing nothing more dramatic than a plume of steam and a warm trickle. A few are throwing ash a mile into the air over an empty stretch of ocean. The number wanders between about 10 and about 40, depending on the day and on how strictly you define the word, but there is never a day with none. Across a whole year, something like 60 to 80 volcanoes erupt somewhere. Over the last 10,000 years, roughly 1,500 land volcanoes have been active at least once, and those are only the ones we can find on the small fraction of the planet that is not underwater. There is something restful in that arithmetic once you sit with it. The world is not usually holding its breath waiting for a catastrophe. The world is simply doing this, continuously, the way a kettle that has been left on a low flame keeps ticking. Almost all of it happens in places where nobody is inconvenienced, and most of it is never reported anywhere, because a mountain quietly glowing in an empty part of the Pacific is not news. While you sleep tonight, several of them will still be at it, patiently in the dark, entirely uninterested in whether anyone is watching. 6. The words active, dormant, and extinct are much vaguer than they sound. An active volcano is usually defined as one that has erupted within the last 10,000 years. That is a generous window, and it is generous for a reason. Volcanoes keep time on a scale that makes our vocabulary look impatient. A mountain that has done nothing since before the pyramids may simply be between appointments. Dormant means sleeping, and it is used for a volcano that has not erupted in living memory but shows every sign of still having a supply of heat underneath. Extinct means the plumbing has been cut off, the heat source has moved elsewhere, and there is no reasonable route back to activity. The trouble is that mountains do not read the labels. Volcanoes considered safely finished have woken after 4,000 years of silence. One in the Philippines had been so quiet for so long that villages had grown comfortably up its slopes. And when it returned, it produced one of the largest eruptions of the century. So the honest version is this. Some volcanoes are working. Some are resting. Some are almost certainly done. And the boundary between the second group and the third group is drawn in pencil by people who freely admit that they are guessing about a machine whose ordinary rhythm is longer than recorded history. 7. Volcanoes are older than every mountain range now standing on the earth. The Alps are young, a few tens of millions of years. The Himalayas are younger still and continue to rise. The Rockies and the Andes are middle-aged by geological standards. Even the worn stumps of the Appalachians, which were once as tall as anything on the planet, are barely 300 million years old. Volcanic activity, by contrast, has been going on since there was a crust to break through, which is somewhere north of 4 billion years. It is the planet's longest-running habit. Continents have gathered and split apart and gathered again. Oceans have opened and closed. Whole categories of living things have appeared and gone. And through all of it, there has never been a stretch of time without something, somewhere, venting heat to the sky. That gives the subject a particular flavor. When you watch a volcano, you are not watching an event. You are watching a process briefly visible that started before there were rocks with fossils in them and shows no sign of finishing. The mountain you are looking at is temporary. The behavior is not. In 10 million years, that specific peak will likely be gone, eroded to a stub or collapsed into a bay, and somewhere else on a coastline that does not yet exist, another one will be doing precisely the same thing in precisely the same way, out of the same heat. 8. Most volcanic activity on this planet happens underwater, and almost nobody sees any of it. Running down the center of the Atlantic and around through the Indian Ocean and the Pacific is a continuous seam where the seafloor is pulling apart and new crust is being made to fill the gap. That seam is a volcano roughly 40,000 miles long. It erupts constantly, in small, quiet increments, mostly under a mile or two of cold seawater. And it produces far more new rock every year than every land volcano put together. Estimates vary, but something like 3/4 of all the melted rock that reaches the surface of the earth reaches it down there in the dark, where the pressure is so great and the water so cold that the lava barely gets a chance to be dramatic. It squeezes out in rounded lobes, chills instantly on the outside, and piles up in stacked gray pillows. Which means the great majority of the planet's volcanic behavior has never been witnessed by anyone. We know it is happening from the contours of the seafloor, from what the seawater carries, and from listening. Underwater microphones pick up the low groans and cracks of submarine eruptions from thousands of miles away. And researchers sometimes catch one beginning without ever knowing exactly which spot on the ridge produced it. There is a whole hidden mountain range down there, longer than any range on land, with almost no name on any of it. 9. The crust that all of this has to break through is astonishingly thin. Under the oceans, it is generally about 4 miles thick. Under the continents, it averages around 25 miles, reaching perhaps 40 under the highest mountains. Set that against a planet whose radius is nearly 4,000 miles, and the proportions become clear. The usual comparison is an eggshell, and the usual comparison is too generous. Take an ordinary egg. Its shell is roughly 1 part in 100 of its width. The Earth's crust, measured against the whole planet, is thinner than that, particularly under the sea. If you shrank the Earth to the size of an apple, the crust would be considerably thinner than the apple's skin. Everything you have ever known sits on that skin. Every city, every forest, every road, every ocean basin, every fossil, every ruin, every conversation. Beneath it lie 1,800 miles of hot, slowly moving rock, and beneath that a core of iron and nickel with an outer part that is genuinely liquid and an inner part squeezed solid again by the weight of everything above. The deepest hole anyone has ever drilled went a little over 7.5 miles down, took about 20 years, and did not get out of the crust. The bottom of that hole was hotter than anyone had predicted, and the rock there behaved more like plastic than stone, and eventually the project simply stopped. 10. The word volcano comes from a small island north of Sicily. The Romans called it Volcano, after Vulcan, their god of fire and metalworking, the smith who made armor and thunderbolts and lived, according to the story, in a workshop beneath the ground. The island smoked. It smelled of sulfur. Occasionally it threw glowing stones into the sea. To sailors passing at night, a forge under the flagstones of the world was not a wild explanation, but the obvious one. That name spread outward until it covered every mountain of its kind anywhere, and from it we also took vulcanize. The process of treating rubber with heat and sulfur, which is a nicely direct piece of inheritance. Other cultures named the same idea from their own experience. In Iceland, the mountains carry plain descriptive names about ice and ash and shape. In Hawaii, the words for the two main kinds of lava are still the Hawaiian words used by scientists everywhere in the world, because the people who lived beside those flows had already made the distinction that mattered and had already named it well. There is a small pleasure in that. The technical vocabulary of one of the oldest sciences is a mixture of Roman mythology and Polynesian observation, and neither part has ever been improved upon enough to be worth replacing. 11. Roughly half of the Earth's internal heat is left over from the day it was made. That is a remarkable thing to keep. A planet is an enormous object, and enormous objects hold warmth for an extraordinarily long time, because heat escapes only through the surface while it is stored throughout the whole volume. Double the size of something, and you multiply its interior far faster than you multiply its skin, so the bigger a hot thing is, the slower it can possibly cool. The Earth has therefore been cooling for the whole of that span, and is still nowhere near finished. The warmth of the original assembly, the great collision that made the moon, the sinking of heavy iron toward the center, all of that energy went into the interior, and much of it is still there. The other half comes from radioactivity. Uranium, thorium, and a particular kind of potassium are spread thinly through the rock, and as they decay, they release a small amount of energy each time. Individually, this is nothing. Collectively, across a planet's worth of rock and a planet's worth of time, it is enough to keep the mantle soft and moving. Without that second source, the Earth would have gone cold and geologically dead a long time ago, as Mars largely has. No moving plates, no fresh mountains, no new crust, no recycled minerals, just a quiet, finished rock with weather. The reason our world still rearranges its own face is that it has an internal budget it has not yet spent. 12. The mantle, the great mass of rock between the crust and the core, is solid. It is also flowing. Both of those statements are true at once, and holding them together is the single most useful idea in the whole subject. The rock down there is not a lake of liquid fire. If you could somehow take a piece of it and set it on a table, it would be a hard mineral you could strike with a hammer. Yet given enough heat, enough pressure, and enough time, that same solid rock creeps. The comparison people reach for is a glacier. Ice is unambiguously a solid, and yet a glacier flows downhill, bending around obstacles, cracking at the surface where it moves too fast to bend. Nobody watching a valley glacier for an afternoon would see anything happen. Come back in a century, and the whole thing is traveled. Mantle rock does the same, at a pace of a few inches a year. Hot regions rise, cool regions sink, and vast slow loops turn over inside the planet on cycles lasting hundreds of millions of years. The continents ride passively on top of this, like leaves floating on a pot of very thick soup warming on a very low flame. Only a tiny fraction of the mantle is ever melted at any moment, perhaps a fraction of a percent. Volcanoes are fed by that fraction, and that fraction is enough. 13. Molten rock arrives at the surface at between about 700 and 1300 degrees Celsius, which is roughly 1300 to 2400 degrees Fahrenheit. For comparison, a household oven at its maximum reaches about 250 Celsius. A wood fire in a grate runs perhaps 600. Molten glass in a workshop sits around 1100, so the coolest lava is hotter than any ordinary fire you have ever sat beside, and the hottest is in the range where iron begins to glow bright orange. The temperature depends on what the rock is made of. Basalt, the dark iron-rich stuff that builds the ocean floor and the Hawaiian Islands, comes out at the hot end, around 11 to 1300. Rhyolite, the pale silica-rich material that feeds the great explosive volcanoes, is much cooler, sometimes only 700, and yet it is far more dangerous. Because temperature is not what makes an eruption violent. You can see the temperature by eye if you know the code. Rock glowing yellow-white is at the top of the range. Bright orange is a little cooler. Deep red is cooler again. A dull cherry red crust means the surface has already lost several hundred degrees, even though what lies an inch beneath it is still fully molten and will stay that way for days. Photographers who work near active flows learn to read the color before the instruments confirm it. 14. There is probably no such thing as an underground lake of lava sitting in a cavern, waiting. That image comes from illustrations in old books, and it is almost entirely wrong. What actually sits beneath most volcanoes is better described as mush, a body of hot rock that is mostly crystals with melted material filling the spaces between them, like a slush of ice and water, or wet sand where the tide has just left it. For decades, this was a genuine puzzle. Instruments could detect a warm region under a volcano, but they consistently found far too little pure liquid to explain the eruptions those volcanoes produced. The resolution was that the melt does not wait around in a single reservoir. It is distributed through a large mushy zone, and it gathers into a genuinely liquid pocket only shortly before it moves, sometimes only weeks or months before. That gathering is what monitoring teams are watching for. A mush that has been quietly sitting for centuries can begin to organize itself, the liquid fraction can rise and collect, and the whole system can go from unremarkable to ready in a period short enough that a person could notice it. Which is oddly comforting. The mountain is not holding a full glass over your head for 10,000 years. Most of the time it is holding damp gravel, and the glass has to be assembled first, and assembling it makes noise. 15. Some magma waits underground for thousands of years before it comes out, and some is made and erupted within a few decades. Crystals record the difference. As melted rock cools, it grows crystals, and those crystals grow in layers like the rings of a tree or the bands in a stalagmite. Each layer preserves the chemistry of the melt at the moment it formed. A crystal that has been sitting in a magma body for a long time has many fine layers. One that formed quickly has few. By slicing those crystals and measuring how far certain elements have spread between the layers geologists can read a rough calendar out of them. The answers have been startling. Some crystals in a well-studied eruption had been sitting quietly for some 30,000 years and then were disturbed only in the last few decades before the mountain woke. The disturbance is usually a recharge. A fresh pulse of hotter material arrives from below, pushes into the cool crystal-rich mush, warms it, remelts some of it, adds gas, and increases the pressure. The system that had been dozing since before agriculture suddenly has an incentive. So a volcano's timeable has two clocks running at once, a long, slow one that feels the system across ages, and a short, sharp one that starts when something new arrives from underneath. We tend to only notice the second. 16. The Earth is quietly leaking about 47 trillion watts of heat into space. All the time, everywhere, that number is difficult to feel. Spread over the whole surface, it is remarkably small, less than 1/10 of a watt per square yard, thousands of times weaker than the sunlight that falls on the same patch at noon. You cannot feel it with your hand. It will never warm a room. Stand in a field on a cold night and every bit of warmth you sense is coming from the sun's leftovers, not from below. And yet, added up over the entire planet, it is roughly twice the total energy that all of humanity uses, from every power station, engine, furnace, and fire combined. It has been running at something like that rate for longer than there have been continents. Most of it seeps out invisibly by conduction, simply warming the rock above until the warmth reaches the surface and radiates away. Only a small share travels the dramatic route, riding up inside melted rock and arriving in daylight as lava. In a few places the leak concentrates: Iceland, Kamchatka, the Rift Valley, the volcanic belt of Japan, the mountains of the Andes. Those are the seams in the coat, the spots where the escaping warmth is not spread thin but funneled, and where you can put your hand on it, or bathe in it, or heat an entire city with it. 17. Some volcanoes sit nowhere near the edge of a plate, and for a long time that made no sense. Hawaii is the classic example. It is thousands of miles from any boundary, right out in the interior of the largest plate on Earth, and it ranks among the most productive volcanic regions on the planet. Iceland is unusual in the other direction, sitting on a spreading ridge and producing far more material than an ordinary stretch of that ridge should. The explanation offered in the 1960s was the hot spot, a narrow column of unusually warm material rising from deep in the mantle, staying more or less fixed in place while the plates slide over the top of it, burning a track through the crust like a candle held under a moving sheet of paper. That model explained a great deal, above all the neat chains of islands and seamounts that get older in one direction. It has since been complicated by better imaging, which shows that some plumes are wide and messy rather than narrow and tidy, and that a few may not come from anywhere near the core at all. The debate continues politely and slowly in the manner of arguments about things that will not be settled in anyone's career. Meanwhile, the hot spots carry on doing exactly what they have done for many millions of years, indifferent to the paperwork. 18. Almost everything about a volcano's personality comes down to one ingredient, and that ingredient is silica. Silica is silicon and oxygen, the same pairing that makes ordinary sand and window glass. Melted rock contains it in quantities from about 45% up to about 75%, and that range is the difference between a mountain that pours and a mountain that bursts. The reason is that silica molecules link arms. At low silica content, the melt is loose and mobile, roughly the consistency of warm treacle, and gas can bubble up through it and escape without difficulty. Such lava runs downhill in rivers, builds broad, gentle slopes, and produces the calm, glowing flows people travel to see. At high silica content, the melt is stiff. The molecules have joined into long chains and networks, and the whole thing behaves less like syrup and more like cold dough or half-set glue. Gas cannot get out. It stays trapped, pressure builds behind a plug of sticky material, and when the plug finally gives way, the release is violent. So the mildest volcanoes and the fiercest ones are made of the same elements in different proportions. It is not a matter of temper or age or size. It is a recipe, and you can predict most of the behavior from the recipe alone. 19. Gas is the engine of an eruption. The rock is only the passenger. Dissolved in magma under pressure is a surprising quantity of volatile material. Water vapor makes up the majority, typically 60 to 90% of the total. Then carbon dioxide, then sulfur dioxide, then smaller amounts of hydrogen sulfide, hydrogen chloride, and fluorine compounds. A body of magma may be a few percent gas by weight, which sounds trivial until you remember what gas does when it stops being compressed. As magma rises, the pressure holding that gas in solution falls away and bubbles form. Bubbles take up vastly more room than the dissolved material did, so the mixture expands, and expanding makes it rise faster, and rising faster drops the pressure further, which makes more bubbles. The process feeds itself. In runny magma, the bubbles simply rise and pop, and you get fountains and rivers. In sticky magma, they cannot escape, so they grow while trapped, until the rock around them is more foam than solid and finally tears itself apart. The material that comes out is that foam, shredded into fragments and flung upward. Pumice is the leftover evidence. Pick up a piece, and you are holding a snapshot of the instant when a gas bubble expanded faster than the rock around it could resist, frozen mid-stretch, light enough to float. 20. Magma does not travel straight up. It travels sideways more often than not. Underneath a volcano there is a plumbing system, and like the plumbing in an old building, it is a mess of pipes fitted at different times for different reasons. Vertical sheets of rock called dikes formed where magma forced its way into a crack and set. Horizontal sheets called sills, where it slipped between existing layers and spread out like jam in a sponge cake. Chambers, conduits, dead ends, and abandoned routes. Magma will always take the easiest available path, and the easiest path is frequently not the shortest. There are documented cases of magma moving more than 30 miles horizontally underground before finding somewhere to surface, so that the eruption happened in a place with no mountain at all, while the mountain everyone was watching stayed quiet. Instruments can follow this. Moving magma cracks rock as it goes, and cracking rock makes tiny earthquakes, so a swarm of small tremors will migrate across a map over days or weeks, tracing the route. Watching one of those swarms travel is among the stranger experiences in the science, because you are seeing something invisible a mile down, drawing a line toward an exit that nobody can predict with confidence. The old picture of a straight chimney under a cone belongs with the cavern of liquid fire. Real volcanoes are branching, opportunistic, and untidy. 21. The outer shell of the Earth is broken into about 15 large pieces and several dozen small ones, and every one of them is moving. They move at roughly the speed your fingernails grow. An inch or two a year for the slow ones, 4 or 5 inches for the quickest. That is so gentle that no one noticed for the whole of human history. And when it was first proposed seriously in the early 1900s, it was rejected for half a century, largely because nobody could suggest a plausible engine. The engine turned out to be the slow churning of the mantle underneath, combined with the simple weight of cold heavy plate edges sinking under their own density and pulling the rest along behind them. Once that was understood, everything else fell into place at once, which is what a good idea does. At an inch a year, a plate travels about 16 miles in 1,000,000 years. Over 50 million years, that is 800 miles. Over 200 million years, the width of an ocean. The Atlantic did not exist when the first dinosaurs walked, and every inch of its floor has been manufactured since, in small nightly increments at a seam down its middle. Nearly every volcano on Earth sits where these moving pieces meet, either pulling apart or pushing together. The map of the world's volcanoes is almost exactly the map of the plate edges, which is why that map looks so strangely organized long before anybody understood why. 22. Where one plate slides beneath another, the world builds its most explosive mountains, and it does it with water. The process is called subduction. A slab of cold, dense ocean floor bends downward and descends into the mantle at a shallow angle, carrying with it everything it has picked up over its lifetime, including a large quantity of water locked inside its minerals and its sediments. As the slab sinks, it warms, and at a depth of roughly 70 miles, the pressure and temperature squeeze that water out. The water rises into the hot mantle rock above the slab, and because water lowers the melting point of rock dramatically, that mantle rock begins to melt when it otherwise would not have. The new melt rises, gathers, mixes with the crust it passes through, picks up silica as it travels, and arrives beneath the surface stiff and gassy and reluctant. This is why the volcanoes above subduction zones are the steep, photogenic cones with a habit of sudden violence, while the volcanoes of Hawaii, fed directly from below with no slab involved, are broad and mild. The whole arrangement is a kind of enormous distillation apparatus. The ocean floor goes down wet and 100 miles away and a few million years later. A mountain in Japan or Chile or Indonesia exhales the water it was carrying. 23. 3/4 of the world's land volcanoes stand in a single horseshoe around one ocean. The Ring of Fire runs about 25,000 miles up the western edge of South America, along Central America and Mexico, through California and Oregon and Washington, out along the Arc of Alaska and the Aleutians, down through Kamchatka and the Kurils to Japan, then to the Philippines, Indonesia, New Guinea, the island arcs of the Southwest Pacific, and finally to New Zealand. It is not a ring in any geometric sense. It is a horseshoe with an untidy opening in the south, and it exists because the Pacific Plate and its neighbors are being consumed around almost their entire margin. Ocean floor is manufactured along the center of that ocean and swallowed at its edges, and the swallowing is what makes the fire. Something like 90% of the world's earthquakes happen along the same line, from the same cause, and the two facts have the same single cause. If you look at a globe with the Pacific facing you, the ring is immediately visible as a rim of small triangles around a great blue field. Some 450 volcanoes are marked on it. Tonight, a handful of them are glowing, and the vast majority of the people living within sight of one are asleep, having long since stopped finding it remarkable. 24. The longest mountain range on Earth is one that almost no one has ever seen. The mid-ocean ridge system winds through every ocean basin like the seam on a baseball, about 40,000 miles from end to end. It is a continuous chain of volcanic mountains, in places 2 miles high, and it is submerged along nearly its entire length. At the ridge, two plates are pulling apart, and hot mantle rock rises to fill the space. As it rises, the pressure on it drops, so it melts, and the melt erupts along the crack and freezes into new ocean floor. Then the plates part a little more, and it happens again and again and again for as long as the ocean has been opening. This means the seafloor is arranged in stripes of age. Newest at the ridge, older with distance, oldest at the far edges against the continents. The pattern is symmetrical on both sides, and the rocks record the flips of the Earth's magnetic field as they cool, so the ocean floor carries a matching barcode on either side of the seam. That barcode, read in the 1960s, was the evidence that finally proved the continents move. The most important discovery in the history of geology was made by towing a magnetometer behind a ship, in the dark, over a mountain range nobody could see. 25. Iceland is a piece of the mid-ocean ridge that grew tall enough to breathe. The island sits directly on the seam of the Atlantic, where Europe and North America are separating at about an inch a year, and it also sits over a hot spot of unusually warm mantle. Ridge plus plume produces far more melted rock than either would alone, and the pile has grown high enough to stand above the water. What results is a country made entirely of volcano. There are roughly 30 active systems on an island the size of Kentucky. The land is splitting down the middle, and in one national park you can walk in a rift valley with the edge of one continent on your left and the edge of another on your right, and a clear, cold lake in the crack between them. Iceland does not merely tolerate this, it runs on it. 9/10 of the country's homes are heated with water that came out of the ground already hot. The capital keeps some of its pavements ice-free in winter by running that same water under the stones. Greenhouses lit and warmed by volcanic heat grow bananas within sight of the Arctic, which is a slightly absurd thing to be true, and is. 26. There is a place in East Africa where a continent is very slowly coming apart. The East African Rift runs some 3,000 miles from the Red Sea down through Ethiopia, Kenya, Tanzania, and beyond. The crust there is stretching, thinning and dropping in long steps, forming the deep valleys in the string of extraordinary lakes. And the thinning allows melted rock up from below. That is the source of the great volcanoes of the region. Kilimanjaro, standing alone above the plain with snow at its top and equatorial heat at its foot. Mount Kenya, worn down to a jagged core. The Virunga chain with its lava lakes. And, in the Ethiopian desert, one of the lowest and strangest volcanic areas on the planet, where the ground is below sea level and colored yellow and green with sulfur salts. Given 10 or 20 million years, the stretching may go far enough to let the ocean in, and the eastern strip of Africa will become a long island with a new sea between it and the rest of the continent, exactly as Arabia has already parted from Africa along the Red Sea. We are watching the first act of an ocean. It is simply that the play is very long, and we came in during the opening minutes. 27. The Hawaiian Islands are a conveyor belt, and they get older as you travel northwest. The Big Island at the southeastern end is the youngest, still growing, still erupting. Maui is older and quieter. Oahu older still. Kauai, further northwest, has been eroded into knife-edged ridges and deep green valleys by rain working on rock that has had no fresh material for millions of years. Continue past the last inhabited island, and the chain does not stop. It carries on as a line of submerged seamounts, sinking and worn flat, running northwest for another 1,500 miles. Then, abruptly, it bends northward and continues as the Emperor's seamounts, as far as the trench off Kamchatka, where the oldest of them are finally being swallowed. The whole chain is a single record of one fixed hotspot and one moving plate, written over 80 million years. The bend, which happened around 50 million years ago, marks either a change in the plate's direction or a wander of the plume itself, and the argument about which is still gently ongoing. And the chain has a future as well as a past. Southeast of the Big Island, under about 3,000 feet of water, a new seamount is already building. Given another 20 or 30,000 years, it will reach the surface and become the next island. 28. The same kind of hotspot has burned a track across the western United States, and the track ends at Yellowstone. Follow the Snake River Plain in Idaho on a map. It is a broad, smooth arc of low ground cutting across otherwise rugged country, and along it lie the remains of a series of enormous volcanic centers, getting steadily younger toward the northeast until they arrive at the corner of Wyoming where the geysers are. The plate is drifting southwest over a fixed source of heat, so the heat appears to march northeast. Each center in its turn produced huge eruptions, collapsed, went quiet, and was carried away, and the plain was left flattened and filled with later lava. Yellowstone is the current position of that track. Its famous features are all one thing seen in different forms. Groundwater sinking into hot rock, heating, and finding its way back up. Geysers where the plumbing constricts and the water flashes to steam. Hot springs where the route is open. Mud pots where there is more acid than water. Terraces where dissolved limestone comes back out of solution in the cold air. The park is not sitting next to a volcano. The park is inside one, standing in a bowl some 30 by 40, 5 miles across, which is why nobody driving through it can see the edges. 29. Where an ocean plate sinks beneath another ocean plate, the volcanoes come up in a curve, and that curve becomes a string of islands. Japan is such a string, 4 large islands and thousands of small ones. With 111 active volcanoes and a national culture that has organized itself around the fact. The Aleutians are another, a long, thin bow of green and gray islands reaching from Alaska almost to Russia across the top of the Pacific. Mostly uninhabited, thoroughly volcanic. The Kurils, the Marianas, the Lesser Antilles in the Caribbean. The Tongan and Vanuatu chains all follow the same design. The reason they curve is geometric. A flat plate bending into a sphere must trace an arc where it enters exactly as a dent pressed into a table tennis ball comes out circular. The line of volcanoes forms parallel to that arc, a set distance behind the trench where the sinking slab reaches the depth at which it releases its water. You can measure the depth of the slab beneath your feet by counting how far you are from the trench, which is a satisfying trick. These arcs are where much of the world's new continental material is manufactured slowly, one island at a time, and then collected and welded onto larger land masses over several 100 million years. 30. Indonesia has more active volcanoes than any other country, and about 130 of them. The archipelago sits where several plates converge, so it is threaded end to end with fire mountains, from Sumatra through Java and Bali and onward through the eastern islands. Java alone has more than 40, several of them within an easy drive of a city. That would sound like an unfortunate address, and the reverse is true. Java is among the most densely populated places on Earth, with some 150 million people on an island roughly the size of England, and the reason is the soil. Volcanic ash weathers into an exceptionally rich earth, and rice grown on those terrace slopes can produce 2 or 3 harvests a year where ordinary land manages one. So the mountains that occasionally take are also the mountains that continually give, and the arithmetic has favored staying for a great many centuries. Villages sit high on the flanks. Farmers walk out at dawn with the summit steaming behind them and think about it no more than a coastal fisherman thinks about the tide. There is a whole philosophy in that, and it does not need to be spelled out. It is simply what the terraces look like from the air, green step above green step, right up to the edge of the ash. Let us pause there for a moment at the 30th and let the map settle. You have now been given the whole framework, and it is a small one. Heat inside. Rock that flows without melting. A thin cracked shell riding on top of it. A few places where melt is made, either because something rose and the pressure came off it, or because water was carried down and lowered the melting point of the rock it met. Everything else in this evening is decoration on those 4 ideas. If you are still awake, you already know enough to look at a map of the world's volcanoes and understand why they are arranged as they are, which is more than any scholar on Earth could have told you 200 years ago. So loosen your grip on it now. Let it go a little. Check your jaw again, because it has probably tightened since I last mentioned it. Let your tongue rest away from the roof of your mouth. Let your eyebrows go, and the small muscles around your eyes which have been working all day and will not be needed again until morning. Feel the weight of the blanket. Feel where your heels rest, and your hips, and the back of your head, and notice that the bed is holding all of it without any help from you whatsoever. You may let it do that entirely. There is nothing left in this evening that requires holding. Think of that island again, if it helps. The sea going in and out over the black rocks. The glow rising and settling behind the shoulder of the hill. The warm ground. Nobody hurrying anywhere. Breathe out slowly and let the out-breath be a little longer than the in-breath, and do not make a project of it. We are going to spend the next stretch on the shapes that volcanoes take, and then on the material they produce, and I promise you that none of it is urgent. Great slow mountains built out of runny rock, small cones that grew in a farmer's field, craters that are not holes blown out, but ceilings fallen in. Then lava itself, its speeds and colors and the tunnels it builds for itself to travel through. Stay if you like. Drift if you like. Either is a good outcome from here. 31. The largest volcanoes on the planet are also the flattest, and you can stand on one without realizing you have climbed anything. Shield volcanoes are built from runny lava that travels a long distance before it stops, so instead of piling up steeply, it spreads. Layer on layer, flow on flow, you get a very broad dome with slopes of only 4 or 5 degrees. The shape of a warrior's shield laid face up on the ground, which is where the name comes from. Mauna Loa on the island of Hawaii is the classic. From its base on the seafloor to its summit is more than 9 miles of accumulated rock, and it covers an area larger than the whole state of Rhode Island. Its neighbor, Mauna Kea, measured from that same seafloor base. Stands about 33,000 feet, which is more than 4,000 feet taller than Everest measured from its own base at sea level. Everest wins on altitude because it starts on a plateau that is already 3 miles up. Mauna Kea wins on actual height because most of it is underwater and nobody thinks to include the part they cannot see. Driving up a shield volcano is a peculiar experience. The road climbs for an hour and a half with no sense of ascent, the slopes so gentle and so consistent that only the thinning air and the disappearing trees give it away, and then the summit arrives as an anticlimax and a very long view. 32. The volcano of children's drawings, the perfect steep cone with a neat crater at the top, is called a stratovolcano, and it is built out of alternating layers. The word strato refers to those layers. A sticky eruption throws out ash, which settles as a soft blanket. A later, runnier eruption sends a lava flow over the top, which sets hard. Then more ash, then more lava, then more ash again, and across a very long run of centuries the alternation builds a steep and surprisingly strong structure, because the hard layers hold the soft ones in place. Fuji is the postcard example, close to symmetrical, snow-capped for much of the year, and quiet since 1707. Mayon in the Philippines is even more perfectly conical. Cotopaxi in Ecuador, Osorno in Chile, Shishaldin in the Aleutians, all of them share the shape. These are the mountains fed by subduction, which means they are fed by stiff, gassy magma, which means they are the ones that build slowly and then rearrange themselves suddenly. The steep beauty and a temperament come from the same recipe. A mountain cannot be that shape without being made of the material that makes it that shape. Almost every volcano that has ever appeared on a stamp, a banknote, or a tourist poster belongs to this family. 33. The smallest volcanoes are the cinder cones, and one of them once grew in a farmer's field while he watched. A cinder cone forms when gassy lava is thrown up in fragments that cool in the air and land as loose, crumbly cinders. They pile up around the vent at the steepest angle loose material can hold, about 30 degrees, making a neat little hill with a bowl at the top, rarely more than 1,000 feet high. They are also the fastest volcanoes to build. Most form in a single eruptive episode lasting weeks to years, then stop forever. In February of 1943, in the Mexican state of Michoacan, a farmer was preparing a cornfield when the ground opened. Within a day there was a cone several yards high. Within a week it was 5 stories. Within a year it was over 1,000 feet, and it had swallowed 2 villages, whose people had been able to walk away in good time. The volcano, named Paracutin after one of them, carried on for 9 years and then went quiet for good. A church tower still stands up out of the black rock where one of those villages was, the stone tower rising from a frozen sea of lava, and people drive out to look at it. It is the only volcano in the world whose entire life, from first crack to final silence, was watched and recorded from beginning to end. 34. The biggest volcanic craters are not blown out, they fall in. When a very large eruption empties a magma body quickly, the roof over that emptied space has nothing left to rest on, and it collapses. What is left behind is a caldera, a broad circular basin often miles across, with steep inner walls and a floor made of the sunken ground. Crater Lake in Oregon is one of the most beautiful. About 7,700 years ago, a mountain of perhaps 12,000 feet, known now as Mount Mazama, erupted enormously and dropped into its own emptied cellar. Rain and snow filled the hole over the following centuries. The lake is 5 miles across, the deepest in the United States at nearly 2,000 feet, and it has no river running in or out. So the water is astonishingly clear and in almost unreal blue. Santorini in the Aegean is another, drowned by the sea rather than by rain, so that ships sail right inside the collapsed volcano, and more beneath cliffs of layered ash with white villages along the rim. The people of the region have a legend about a great island that vanished. It is not hard to see how a story like that starts when the evidence is a bay 6 miles wide with a small black cone still steaming in the middle of it. 35. The word supervolcano was invented by a television program, and geologists have been mildly resigned to it ever since. The technical measure is the Volcanic Explosivity Index, a scale from 0 to 8. And it works logarithmically, so each step means roughly 10 times more material. A gentle Hawaiian flow is a 0 or a 1. A textbook cone eruption is a 3 or a 4. Mount St. Helens in 1980 was a 5. Pinatubo in 1991 was a 6. Tambora in 1815 was a 7. And 8 requires more than 240 cubic miles of erupted material, and that is what earns the television name. There have been perhaps a few dozen in the last few million years, and none in recorded human history. These events do not build mountains. They remove them, leaving only the wide collapsed basin. Yellowstone has produced 3, the most recent about 640,000 years ago. Toba in Sumatra produced one about 74,000 years ago, the largest known in the last 2 million years. It is worth being clear about the odds, because the word has done some damage. The average interval between such events is measured in tens of millennia, and the current systems are all well instrumented and thoroughly quiet, and nothing about the geology suggests anything is due. It is a fine thing to find interesting and a poor thing to worry about at night. 36. Some of the largest eruptions in history came out of long cracks in the ground rather than out of a peak. A fissure eruption opens as a line, sometimes miles long, and lava rises along the whole length of it at once. The result, seen from a distance in the dark, is a curtain of fire. A wall of bright fountains standing side by side, sometimes hundreds of feet tall, with the flames of the fountains overlapping into a continuous glowing ribbon. Iceland specializes in these. In 1783, a fissure named Lake opened for about 16 miles and erupted almost continuously for 8 months, producing more than 3 cubic miles of lava. The largest such flow in recorded history. The gases from it drifted across Europe as a persistent dry haze, dimming the sun and damaging crops from Ireland to Italy. More recently, the peninsula southwest of Reykjavik reawakened after some 800 years, opening fissure after fissure across bare ground within sight of the airport, and drawing crowds of people who walked out over the moss with thermoses to sit on a ridge and watch it in the cold. Curtains of fire tend to be the gentlest kind of large eruption to be near, because the material is runny and the gas escapes freely. They are noisy, bright, and mostly indifferent to observers standing a safe distance upwind. 37. Some lava is too stiff to flow anywhere at all, so it simply piles up over its own vent like toothpaste squeezed from a tube. That pile is a lava dome. The material is so viscous and so cool, sometimes only 700 degrees, that it moves at inches per day and holds together as a heap of rubble and steep-sided rock, growing from the inside as more is pushed up beneath it. Domes can rise hundreds of feet in a few months, and then sit there for decades, cracking, steaming, and slowly cooling. Mount St. Helens grew one in its crater after 1980, and then grew another between 2004 and 2008, this second one arriving as a solid spine of rock that emerged like a fin, pushing up several feet a day, crumbling at its edges as it came. Cameras watched it. It looked like nothing else, a slab of gray mountain being extruded out of the crater floor. Domes are the sign of the stickiest material, and they are unstable. If gas builds up beneath one, or if part of one collapses, the sudden release can send hot ash and rock down the slope. So volcanologists watch them attentively while also finding them beautiful, which is the ordinary condition of the profession. Some domes are ancient. Round, steep hills in old volcanic districts, wooded now and quite unremarkable, are frequently domes that stopped moving a very long time ago. 38. Some of the calmest lakes in Europe sit in craters made by a single blast of steam. When rising magma meets groundwater, the water flashes to steam instantly, expanding many hundreds of times. And the result is a shallow, wide crater blown out of flat ground with almost no cone around it. These are called maars, from a word used by the people of the Eifel region of Germany, where dozens of them lie in green farmland. Most of them have since filled with water, and they are now round, deep, quiet lakes with reeds around the edge and rowing boats pulled up on the grass. Nobody swimming in one on a summer afternoon would suspect its origin. The oldest are hundreds of thousands of years old, the youngest around 11,000. Because maar lakes are steep-sided and undisturbed, the sediment at the bottom builds up in fine annual layers undisturbed for 40,000 years. Cores drilled from them give researchers a year-by-year record of climate, pollen, dust, and ash across immense stretches of time, which is the sort of archive that no library holds. So the least dramatic volcanic feature in the landscape turns out to be exceptionally valuable, and it looks, in every photograph, exactly like a pleasant place to have a picnic. 39. Lava that erupts underwater does not spread out. It bulges into rounded lobes, one after another, and stacks them like sacks of grain. The reason is speed of cooling. In cold water, a skin forms on the lava almost immediately, tough and glassy. Molten material continues to arrive inside that skin, inflating it like a balloon until the skin splits at a weak point and a new lobe pushes out through the tear, and the process repeats. The result is pillow lava, a slope of rounded gray pillows a yard or two across, packed together with fine glassy rinds. Because this shape forms only underwater, it is a reliable signature. When geologists find pillow lava high in a mountain range on dry land, they know that stretch of rock was once seafloor, and they can say so with real confidence. Pillows have been identified in rocks over 3 billion years old, which is a key piece of evidence that oceans existed extraordinarily early. Divers on the flanks of Hawaii have filmed pillows forming in real time, glowing dull orange through their skins as they stretch. The water immediately around them is heated enough to shimmer, but a few yards away it is simply cold ocean, going about its business. The seafloor of the world is largely made of this. Endless gray pillows, stacked in the dark, quietly waiting to be turned into somebody's mountain range in 100 million years. 40, there are volcanoes that are entirely cold, and they erupt mud. A mud volcano forms where gas, usually methane, works its way up through soft, wet sediment and carries the mud along with it. The mixture spills out at the surface and builds cones, sometimes only a few feet high, sometimes several hundred, with craters that bubble and gurgle and occasionally burp. Azerbaijan has the greatest concentration of them, several hundred on the plains near the Caspian. In a landscape of gray lunar hills, whose ground is always damp and the air smells faintly of gas. Some of them ignite when the methane catches and burn with a pale flame for days. Others simply mutter along, cool enough to put your hand in. They are not volcanoes in any strict sense. No magma is involved, and nothing is melted. But they behave so similarly, building cones and flows and craters out of erupted material, that the name stuck and no one has proposed a better one. Standing among them is a curiously restful experience by all accounts. Gray mounds to the horizon, small popping noises, a slow bubble here and a slow bubble there, and no urgency whatsoever in any direction. 41. There are two kinds of basalt lava surface, and both of them are known worldwide by their Hawaiian names. The first is pahuho. It is smooth, and it cools into ropey folds and coils and wrinkles as though someone had drawn a stick through thick paint and let it set. Walking on old pahuho is easy. It has a glassy sheen, it rings faintly underfoot, and its curves look almost deliberate. The second is It is a chaos of loose, sharp clinker, angular blocks with edges like broken glass, piled several feet deep and completely unwelcoming. Crossing a field of it takes hours and ruins boots. The name is often said to be what a barefoot person would exclaim while attempting it, which is a good story that may or may not survive scrutiny, and either way, it is memorable. The remarkable part is that both come from identical material. A flow can begin as smooth pahuho near the vent and convert to rough further downhill as it cools slightly and is stirred. And the change is one way. Never turns back into pahuho. That these two words are the international scientific terms used in journals in every language is a quiet acknowledgement that the people who lived beside these flows for centuries had already sorted out the classification that mattered, and had already given it names that worked. 42. Lava usually moves slower than a person walking, which is not what films suggest. A typical basalt flow on a gentle slope advances at a few yards an hour. Its front is a crumbling wall of dark rock glowing in the cracks, pushing forward as more material arrives behind. You can stand and watch it, take a photograph, take another, and it will not have moved appreciably between them. Homeowners in Hawaii have had days and sometimes weeks of notice, and have removed furniture at a measured pace while the flow came down the road. Steeper ground and hotter material change that. Flows down a steep slope can manage several miles an hour, quick enough to be a genuine problem, though still not quick enough to catch a car on an open road. The exception is Nyiragongo, in the Democratic Republic of the Congo, which holds an unusually fluid lava in a lake at its summit. Its material is so low in silica that it is thin as engine oil, and when the crater wall has failed the lake, has drained down the mountain at speeds estimated well over 40 miles an hour. It is the fastest lava anyone has measured, and it is fast because of chemistry, not because of temper. For every other volcano on Earth, the honest summary is that lava is a slow problem. 43. Lava rivers build their own roofs and then run through the dark for miles. As a flow moves, its upper surface cools and crusts over, and the crust insulates the still molten material beneath. Once the roof is complete, you have a pipe, and inside that pipe the lava loses almost no heat. So it can travel enormous distances without stiffening. Some tubes have carried material more than 30 miles from the vent. When the supply finally stops, the last of the lava drains out and leaves an empty tunnel. These become caves, and they are excellent caves, with smooth floors and rounded ceilings, and occasionally stalactites made of rock that dripped while it was still molten and set as it fell. There are hundreds of them in Hawaii and Iceland and the Canary Islands, some running for miles, high enough to stand in and wide enough to drive through. People have used them for shelter, for storing food, and for burials. In Iceland, a few are open to visitors, with wooden walkways laid along the floor and small lamps that show ceilings colored red and gold by minerals. Standing in one is peculiarly quiet. Thick rock overhead absorbs sound completely, and there is no wind and no water noise. It is one of the stillest places you can be. 44. The color of glowing lava is a thermometer, and anyone can read it. Around 1,300 degrees Celsius, freshly erupted basalt glows a pale yellow, almost white in the brightest spots. Cool 100 degrees and it moves to a rich orange. Another 100 and it becomes deep orange-red. Below about 700 it is a dull cherry color that fades quickly toward invisible. And by 500 there is only a faint glow you would miss in daylight. This is why photographs of a flow show a black surface laced with bright veins. The exposed skin has already dropped several hundred degrees within seconds of meeting the air and gone dark, while the cracks show what the interior is still doing. The same relationship between temperature and color is used everywhere. A blacksmith judges iron by it. A potter judges a kiln by it. Astronomers judge the temperature of a star by it, which is why blue stars are hotter than red ones despite every color convention on a bathroom tap. So a distant volcano seen from an aircraft, showing a small point of yellow at the vent and a long thread of dimming orange down the slope, is displaying a temperature graph across the mountainside, brightest and hottest at the source, cooling steadily with every mile it travels. 45. A handful of volcanoes hold open lakes of lava that stay liquid for years or decades. There are usually fewer than 10 anywhere in the world at any one time, because keeping a lake open requires a very specific balance. The supply of heat from below must exactly match the loss of heat to the sky, or the surface will freeze over or the lake will drain away. Eta Ale in the Ethiopian desert has held one for over a century. Nyiragongo in the Congo has held one on and off for decades. Kilauea in Hawaii, Erebus down on the Antarctic continent. Ambrim in Vanuatu and Masaya in Nicaragua have all kept one at various times. Watching a lava lake, by every account, is hypnotic rather than frightening. The surface forms a thin, dark crust, which is constantly pulled apart along glowing seams as the material circulates beneath. Plates of crust drift, collide, and are dragged under to be remelted. It is plate tectonics in miniature, playing out over minutes instead of ages, and the same physics is driving both. At night, the whole crater fills with a soft orange light that pulses gently as the lake turns over, and the sound is not a roar, but a series of slow, wet sighs. 46. When lava cools too quickly to organize itself into crystals, it becomes glass. Obsidian is that glass, jet black usually, sometimes with a red or golden sheen, and it breaks along smooth, curved surfaces to leave an edge sharper than surgical steel. A well-struck obsidian blade can be a few molecules thick at its cutting edge, considerably finer than anything that can be ground on metal. Human beings work this out very early and never really stopped. Obsidian tools appear across the ancient world wherever the material could be found or traded, and they are still occasionally used in delicate surgery today, because the incision from a blade that fine heals with less scarring. The glass forms only where the melt is silica-rich, so that the molecules are already tangled, and where cooling is fast enough that they cannot arrange themselves. Given a few thousand years, obsidian slowly absorbs water and begins to crystallize and cloud, so ancient pieces are duller than fresh ones. That process is regular enough that archaeologists once used it as a clock for dating tools. There are obsidian flows you can walk on, great black glassy ridges glittering in the sun, entirely bare of plants, looking less like a landscape than like the leftovers of an enormous industrial accident. 47. Some volcanic rock floats and rafts of it have crossed oceans carrying passengers. Pumice forms when gas-rich froth is thrown out and cools instantly, freezing the bubbles in place. What comes out is a rock that is more whole than solid, light enough to sit on water for months or years until it eventually becomes waterlogged and sinks. After large submarine eruptions, pumice comes up in quantity and gathers into rafts. In 2012, a raft appeared off New Zealand, covering an area estimated at 10,000 square miles. In 2019, another drifted westward from Tonga toward Australia over many months, and by the time it arrived, it was covered in barnacles, corals, algae, and small crabs that had settled on it during the crossing. That is a genuine mechanism for spreading life. Remote islands are colonized partly by seeds and animals that arrive on floating material. And volcanic pumice is unusually good at the job because it lasts, it floats high, and it comes with a rough surface for things to grip. Ships have occasionally sailed into a raft at night and found the sea gone strangely quiet and gray around them, the swell flattened, the hull pushing through what sounded like gravel. Crews describe it as unnerving until somebody works out what it is. 48. Basalt is the most common rock on the surface of this planet, by a very wide margin. Every square mile of ocean floor is made of it, and the ocean floor is 70% of the world. Add the great flood basalt provinces on land and the countless volcanic islands, and it becomes clear that the familiar rocks of the continents, the granites and limestones and sandstones that most people picture, are the minority material. Basalt is dark, fine-grained and heavy, made mostly of two minerals that grow too small to see without a lens. It is also enormously useful. Crushed basalt is the standard aggregate under roads and railway lines across much of the world. Basalt fibre is spun into cloth. Cut basalt paves streets in a dozen European cities where the local hills happen to be volcanic. And it may yet be useful in another way. Basalt reacts with carbon dioxide dissolved in water, turning the gas into solid carbonate minerals over a period of a couple of years, which is startlingly fast in geological terms. Trials in Iceland have pumped carbonated water into basalt underground and found it mineralized far quicker than anyone expected. Which is a neat arrangement. The rock that arrived as a gas-rich melt may end up as a storage cupboard for gas that we would rather not have in the air. 49. A few times in the Earth's history, lava has poured from the ground continuously for hundreds of thousands of years and covered whole regions. These are the flood basalts, and they are the largest volcanic events the planet produces. Not explosions, but an unimaginably persistent outpouring from long fissures, flow upon flow. Each one perhaps tens of yards thick and covering thousands of square miles. Stacked into piles more than a mile deep, the Deccan Traps in western India cover about 200,000 square miles and were laid down around 66 million years ago. The Siberian Traps are larger still and date to about 252 million years ago. The Columbia River basalts in the northwestern United States are younger and smaller and just as impressive to look at. Their stacked layers exposed in the walls of the great river gorges. Both of the older events sit uncomfortably close in time to major turnovers in life on Earth, and the connection is thought to run through the gases released rather than the lava itself. Sulfur first, cooling the world briefly, then carbon dioxide over a longer period, warming it and altering the ocean's chemistry. Today these provinces are simply landscape. Farmland in Maharashtra, wheat country in Washington, endless flat steppe in central Russia, all of it standing on rock that once poured. 50. When a thick sheet of lava cools slowly and evenly, it cracks into columns, and those columns are very often six-sided. The reason is arithmetic. As the sheet cools, it shrinks, and shrinking material must crack somewhere to relieve the tension. Cracks form at regularly spaced points and spread until they meet, and the most efficient way to divide a flat surface into equal areas with the least total crack length is a pattern of hexagons. The same solution appears in drying mud, in cooling porridge, and in a honeycomb, on the same principle. Once the pattern is established at the surface, it propagates downward as the cooling front descends, so the cracks become long vertical columns, sometimes 100 feet tall, packed together like a bundle of pencils. The Giant's Causeway in Northern Ireland is the famous example, 40,000 columns stepping down into the sea. Fingal's Cave on the Scottish island of Staffa is another, a sea cave with columned walls and a roof that produces such particular acoustics from the waves that a composer wrote an overture about it. Devil's Tower in Wyoming, Svartafoss in Iceland, and the cliffs of the Organ Pipes in Australia belong to the same family. Each of those places has a legend attached explaining the stones as the work of giants, which is a fair conclusion from the evidence available at the time. That is 50. We are halfway. If you are still with me, you have traveled from the center of the planet out to the columns of the Giant's Causeway, and you have done it lying down, without moving, in the dark, which is by a wide margin the most comfortable route anyone has ever taken. There is no test at the end of this. Nothing from the first half will be needed in the second. If you have forgotten what silica does, or which lava is smooth and which is rough, that is entirely as it should be, and I will not be asking. Let yourself sink a little further into the mattress now. Notice how heavy your arms have become. Notice that your hands have probably uncurled without being told to. If one shoulder is still holding on, let that one go now, and let the other one follow. Let your legs be long and heavy and completely unemployed. The room around you is doing nothing at all. The house is doing nothing. The street outside is quiet or has whatever noise it always has, and that noise can carry on without your supervision. Somewhere on the far side of the planet, it is the middle of the afternoon, and someone is walking up a black gravel slope with a notebook, checking a thermometer that has been sitting in a fumarole since the spring. That is all that is happening. It has been happening in one form or another for 100 years, and will still be happening when we are all long past caring, and there is something very restful in being one small, quiet part of a very long, very slow, very patient piece of work. In the second half, we will go up into the sky, into ash and haze and strange sunsets, then back through a handful of famous mountains told gently. Then out to the soil and the hot springs and the beaches, and finally off this planet altogether to look at volcanoes made of ice. Then we will come home, and I will let you go. Breathe out. Let the next fact arrive on its own. 51. Volcanic ash is not ash. Nothing has burned. The word is a leftover from an age when people assumed a volcano was a fire, and it is stuck to a material that has nothing in common with the soft gray powder in a grate. What comes out of a volcano is rock and glass, shattered into fragments smaller than 2 millimeters by the force of expanding gas, and each fragment keeps the hard, sharp edges of the break. Under a microscope, it looks like a heap of tiny broken bottles, which is why it behaves so badly. It does not dissolve in rain. It does not soften. It scratches whatever it lands on. It clogs filters and machinery, and it conducts electricity when wet, which is why it interferes with power lines. It is also heavy. A layer of dry ash a few inches deep weighs more per square yard than a comparable depth of snow, and if rain falls on it, the weight can double. Most of the damage to buildings after an ash fall comes from roofs carrying a load they were never designed for. The standard advice in ash country is therefore not to hide indoors and wait, but to go up and sweep the roof repeatedly while it is still falling and still dry. It is the single most useful thing anyone can do, and it is, oddly, domestic. The response to one of the great forces of nature turns out to involve a broom. 52. The biggest ash columns punch straight through the weather and keep going. Ordinary clouds live in the lowest layer of the atmosphere, up to about 7 miles at the equator. Above that lies the stratosphere, where the air is stable and layered and where nothing ordinary rises, which is why airliners cruise at its lower edge in smooth conditions. A large eruption column is buoyant enough to break through that ceiling. Hot gas and fine particles rise in a great churning pillar, entrain air, expand, and can reach 25 miles or more, at which point the column flattens sideways into the classic anvil and begins to spread as a gray umbrella across hundreds of miles. Once material is in the stratosphere, it stays. There is no rain up there to wash it out, so fine particles and sulfur droplets can circle the globe for a year or two before they gradually settle. That is the boundary that matters for climate. An eruption that keeps its material below the weather has local effects and is rained out in weeks. An eruption that reaches above the weather can alter the color of sunsets and the temperature of the whole planet, and can do it from a mountain that nobody in the affected countries has ever heard of. 53. Eruption clouds make their own lightning, and a great deal of it. The mechanism is the same as in a thunderstorm, only the particles are different. In a storm cloud, ice crystals and hailstones collide and exchange charge. In an ash cloud, the colliding particles are rock fragments, tumbling over one another in a violently turbulent column, and the friction separates charge just as effectively. Positive at one end, negative at the other, and eventually the difference becomes too large for the air to hold. The display can be extraordinary. Hundreds of flashes a minute in some cases, threading through a black column, lighting it from within in flickers of white and pink. Some of the finest photographs in the field are of this, taken from a safe distance at night, with the mountain a dark shape and the column above it wired with light. It is also useful. Lightning produces radio noise. And radio noise travels much further than any camera can see and passes straight through cloud cover. A global network of lightning detectors built mainly for storm forecasting will register the flashes of a volcanic column in a remote place, which is sometimes how the world first learns that a particular mountain has begun. An eruption in an empty ocean can be announced essentially by radio static. 54. A single large eruption can cool the entire planet by a measurable amount for 2 or 3 years. The agent is not ash, which falls out quickly, but sulfur. Sulfur dioxide reaching the stratosphere combines with water vapor to make a fine haze of sulfuric acid droplets. And those droplets are excellent at scattering incoming sunlight back into space while allowing the Earth's own heat to escape upward as normal. When Pinatubo erupted in the Philippines in June of 1991, it put roughly 20 million tons of sulfur dioxide into the stratosphere. Over the following months, the haze spread around the world, and global average temperature fell by about 0.5 degrees Celsius, close to 1 degree Fahrenheit, for the next 2 years before recovering. 0.5 degree sounds small. Spread across an entire planet, it is enormous, and it showed up in growing seasons, in river flows, in the extent of sea ice. That event was also a gift to science because it was the first great eruption of the satellite era. Researchers watched the cloud travel, measured its effect, and compared the result with the predictions of climate models, which had forecast the cooling in advance. The models got it right, which did a great deal for confidence in them. 55. 1816 is remembered in Europe and North America as the year without a summer. The cause had arrived the previous April on the other side of the world, when Tambora, on the Indonesian island of Sumbawa, produced the greatest eruption of the last 1,000 years. It removed the top 4,000 feet of its own mountain and put an immense quantity of sulfur into the stratosphere. The following year, the northern hemisphere did not warm properly. Snow fell in New England in June. Frost killed crops in August. In Europe, the summer was cold and relentlessly wet. Harvest failed across several countries, and the price of bread rose to levels that produced unrest in a dozen places. It also produced literature. A group of writers holidaying beside a Swiss lake found themselves shut indoors by weeks of gray rain. And to pass the evenings, they agreed to each write a ghost story. One of the party, then 18 years old, began the tale that became Frankenstein. Another produced the fragment that grew into the modern vampire story. So a mountain in Indonesia altered the harvest of Vermont, the politics of France, and the shape of English fiction in a world that had no way of connecting any of it, and would not make the connection for another century and a half. 56. For years after a great eruption, sunsets go strange. Fine particles high in the atmosphere scatter light in a particular fashion, and the effect is to add color to the sky well after the sun is gone. Ordinary sunsets fade within 20 minutes. Volcanic ones develop a second glow half an hour later, a spreading wash of pink and violet and copper that seems to come from the wrong part of the sky and lingers. After Krakatoa in 1883, these were reported worldwide for 2 years. In several places, the glow on the horizon was mistaken for a distant fire, and fire brigades in more than one town turned out to look for a blaze that was not there. Painters recorded them. Newspapers printed letters from readers trying to describe the colors. A well-known painting from the following decade shows a figure on a bridge under a sky of streaming orange and red. And researchers have argued at length about whether the artist was painting a Krakatoa sky remembered from his youth in Norway. Some say yes, some say it was a different atmospheric effect, and the argument is genial and unresolved. It is a pleasing thought, whichever way it falls. That the residue of an island coming apart in the Sunda Strait drifted around the world, hung in the air over a northern city, and ended up on a wall in a gallery. 57. Hawaii has its own kind of smog, and the local word for it is vog. Volcanic gas leaving a vent is mostly water vapor and carbon dioxide, but the sulfur dioxide within it reacts in sunlight with oxygen and moisture to form fine sulfate droplets. Those droplets hang in the air as a pale haze, softening the outlines of the hills, dulling the blue of the sky, and giving the light a particular milky quality. During long eruptive periods, the trade winds carry it down the chain of islands, and it settles in the lee of the mountains. Residents of the affected districts watch the forecast for it as people elsewhere watch for pollen. It irritates the throat, it is hard on anyone with asthma, and it makes the acid rain that gradually eats through metal roofs and gutters. It also makes for spectacular photographs, which is the recurring bargain of the whole subject. Farmers on the Kona side have long known that certain crops do better in a hazy year, because the diffuse light spreads more evenly through a canopy than direct sun does. Coffee grown in that district is famously good, and the haze is quietly part of the reason. 58. At one Indonesian volcano, the escaping gas burns with a blue flame that can be seen only in darkness. Kawah Ijen in eastern Java vents sulfurous gases at very high temperature through cracks near its crater lake. When that gas meets the oxygen of the air and ignites, it burns electric blue, and the flames run down the rock in sheets that can reach several yards high. Some of the gas condenses before it burns, running as molten sulfur, glowing blue, before setting into bright yellow crystal. It is only visible at night. In daylight, the flames are invisible against the sun, and the crater looks like any other steaming yellow hollow, so visitors climb in the dark hours to see it and are back down by breakfast. The same crater holds a lake of exceptional acidity, a milky turquoise color of remarkable beauty, and men have long worked there carrying baskets of solidified sulfur up the crater wall and down the mountain by hand. Photographs of that work are among the most striking images in the whole field. Sulfur has been mined and used since antiquity, for medicine, for preserving wine, for treating skin, for match heads. Most of it now comes as a byproduct of refining oil, but the volcanic kind is still gathered in a few places in the oldest possible manner. 59. Volcanic ash makes some of the best farmland in the world, and it takes a surprisingly short time to do it. Fresh ash is barren. It is glass, it holds no nitrogen, and it drains too freely. But it is also chemically restless, with an enormous surface area for its weight, and it weathers far faster than solid rock. Within a few decades, rain and microbes have begun releasing potassium, phosphorus, calcium, and magnesium in exactly the forms plants can use, and the resulting soil holds water well and stays loose. Within a century, ground that was sterile gray powder can be the richest land on the continent. Within a few centuries, it is legendary. This is why the slopes of Etna are covered in vineyards and citrus groves, why the Campanian plain around Vesuvius has been the market garden of southern Italy for 2,000 years, why Java carries the population it does, and why the coffee districts of Central America and the tea gardens of the Indonesian highlands sit where they sit. It is the longest standing bargain that human settlement makes with geology. The land gives extravagantly and then, at intervals measured in generations, asks for something back. Every farming culture that lives on a volcano has worked out the terms independently, and every one of them has decided to stay. 60. Ash preserves things. It is the reason we have some of the most intimate records of the ancient world. At Pompeii and Herculaneum, the material that fell in 79 buried streets, houses, gardens, and loaves of bread in a matter of hours and sealed them from air and water. Wooden furniture survived as carbon. Wall paintings kept their color. Scrolls in a private library were preserved as charred cylinders that modern imaging is now, extraordinarily, beginning to read without unrolling them. Where organic material decayed inside, hardened ash it left cavities, and by pouring plaster into those cavities, investigators recovered the exact forms of the animals and people who had been there. Much older still are the footprints at Laetoli in Tanzania. About 3.5 million years ago, a nearby volcano laid down a thin layer of fine ash. Light rain dampened it. 3 individuals walking upright crossed the surface along with hares and guinea fowl and an ancient horse. The sun baked the layer hard, more ash covered it, and the impressions stayed. Those tracks show a heel strike, an arch and a big toe held in line with the others. They are the earliest clear evidence that our ancestors walked as we do, and they exist entirely because a volcano put down a sheet of wet cement at exactly the right moment. 61. The first careful scientific description of an eruption was written by a teenager who watched one from across a bay. In the summer of 79, Vesuvius went from an ordinary green mountain, thickly formed, to a column of ash more than 20 miles high. A 17-year-old was staying at the naval base at Misenum with his mother and his uncle who commanded the fleet. The uncle sailed toward the mountain partly out of curiosity and partly to help evacuate people from the shore, and did not come back. 27 years later, the nephew wrote 2 letters describing the whole thing at the request of a historian friend. He recorded the shape of the column, which he compared to an umbrella pine, broad at the top on a tall trunk. He recorded the sequence of events, the fall of pumice, the darkness, the smell, the tremors, the tide withdrawing, and the behavior of the crowds, including his mother's insistence that he leave without her and his refusal. Those letters are so accurate that volcanologists still use them. The style of eruption that produces a tall, sustained column with a spreading top is called Plinian, after the uncle who died and the nephew who wrote it down. It is a strange kind of immortality. A boy's homework assignment, delivered nearly 3 decades late, became a technical term used in every language in the field. 62. Around 1600 years before the Common Era, a mountain in the Aegean removed most of its own island. Thera, which we call Santorini, erupted with such force that the center of it collapsed into the sea and left the ring of cliffs that stands today. The Bronze Age town on its flank, at Akrotiri, was buried under many yards of pumice and preserved almost completely. Its streets, its multi-story houses, its plumbing, its wall paintings of dolphins and swallows and boats, all of it still there, and remarkably, no bodies and very few valuables, which suggests the people read the warnings and left in good order. The eruption sent tidal waves across the eastern Mediterranean and dropped ash on Crete and beyond. The great Minoan civilization centered on Crete did not end that day, but it declined over the following century and was eventually absorbed. Ever since, People have connected this with the story of a wealthy island civilization that sank beneath the sea in a single day and night. Whether the philosopher who first told that story had heard some distant echo of Thera is entirely unprovable and endlessly discussed. Today the crater is a harbor. Ferries cross it every hour. Cliffs of white and red and black ash rise 900 feet on either side, and the small dark cone in the middle still gives off a faint smell of sulfur. 63. The largest lava flow in recorded history came out of a crack in Iceland and changed the weather in Europe for a year. The Lache fissure opened in June of 1783 and continued for 8 months. It produced enough lava to cover a small country and released an extraordinary quantity of sulfur dioxide and fluorine. Iceland itself suffered terribly, losing most of its livestock to the fluorine poisoning of the grass and a large share of its people to the famine that followed. The gas traveled. Through that summer, a persistent dry blue haze settled over Europe. It was thick enough to blur the sun at midday, hot and still and strangely oppressive, and it was recorded from Scandinavia to Italy. In England, a naturalist wrote about it in his village journal, noting the peculiar coppery color of the sun and how the haze did not clear with rain. Across the continent the following winter was one of the hardest of the century. Crops failed. Rivers froze. A run of poor harvests contributed to the hardship in France that ran over several years toward the events of 1789. None of these people could have known why. The connection between an Icelandic fissure and a French bread queue would not be drawn for almost 200 years. 64. The sound of Krakatoa in 1883 is the loudest noise in the historical record. The volcano stood in the strait between Java and Sumatra. Over 2 days in August, it destroyed itself, and the final event of the 27th was heard clearly at Rodrigues Island in the Indian Ocean, nearly 3,000 miles away, where the harbor master wrote in his log that he had heard the distant roar of heavy guns from the east and sent men to look for a ship in distress. 3,000 miles is the distance from London to the Caspian Sea, or from New York to the coast of Ireland. The sound was reported across roughly 1/13 of the surface of the planet. Closer in, the pressure wave was strong enough to be recorded on barographs in every country that had one. Those instruments show the wave passing, then passing again from the other direction, having gone around the world, then again and again for 7 complete circuits over the following 5 days. The island was reduced to fragments, and the sea took the rest. Then, 44 years later, fishermen noticed steam rising from the water at the same spot, and a new cone broke the surface. It is called Anak Krakatoa, the child of Krakatoa, and it has been growing ever since. 65. The largest eruption of the 20th century happened in a valley with nobody in it, and it took years for anyone to work out where it had come from. In June of 1912, at the base of the Alaska Peninsula, a vent called Novarupta produced about 3 cubic miles of material in 60 hours. That is roughly 30 times the volume of Mount St. Helens. Ash fell a foot deep on Kodiak Island 100 miles away, where for 3 days it was too dark at noon to read a watch held at arm's length, and yet not one person is known to have died. An expedition sent in 4 years later crossed a ridge and found a wide valley floor pierced by thousands of steaming vents, some of them hundreds of feet high, the whole basin hissing gently in the cold air. They named it the Valley of 10,000 Smokes, and their photographs made it famous and a national monument was created to protect it. The smokes were not permanent. They were the last heat escaping from the enormous sheet of hot ash that had filled the valley, and within a couple of decades they had faded away. Curiously, the eruption came from a small new vent several miles from the mountain that collapsed, which is a textbook case of magma traveling sideways before it finds a door. 66. On the morning of the 18th of May, 1980, a mountain in Washington state went sideways. Mount St. Helens had been swelling for 2 months. A bulge had grown on its northern flank at a rate of 5 feet a day, pushed out by magma rising inside, and the whole side of the mountain had become unstable. An earthquake shook it loose, and the entire north face slid away in the largest landslide ever witnessed. That removed the lid. The pressurized material inside, no longer contained, expanded outward rather than upward, and a hot cloud swept north across 230 square miles of forest, laying down mature trees in neat parallel rows like combed hair. The summit lost 1,300 feet. What has happened since is the more interesting half of the story. Biologists were given an entire landscape reset to bare gray, and they have watched it recover ever since. Plants returned faster than anyone predicted, largely because pockets survived under late spring snow. Gophers, safely underground that morning, came up and mixed buried soil with new ash. Elk walked in within weeks and left tracks that caught seeds. 40 years on it is a young forest with lakes and meadows and the finest natural laboratory of its kind anywhere. 67. In 1991, a mountain in the Philippines was correctly predicted, and tens of thousands of people walked away in time. Pinatubo had been quiet for about 500 years, long enough that its slopes were forested and settled, and that it appeared on few lists of concern. In April, steam vents opened. A joint team of Filipino and American scientists moved in with instruments, and over 8 weeks they tracked swelling ground, rising sulfur output, and migrating earthquakes. They produced a set of alert levels and a simple map of concentric zones, and they explained it repeatedly to local officials, to a nearby air base, and to villages on the flanks, including showing a plainly made film about what the hazards actually looked like. Evacuations widened in stages as the signs strengthened. On the 15th of June, the mountain produced the second largest eruption of the century. A typhoon arrived on the same day, which soaked the falling ash and collapsed many roofs. It was a hard event by any measure. It would have been a vastly harder one without the 8 weeks of work that preceded it, and the estimates of lives saved run to the tens of thousands. That episode is the profession's proudest case, and it is taught everywhere because it demonstrated the entire chain working: instruments, interpretation, communication, and people willing to leave their homes on the strength of a stranger's map. 68. In 2010, a modest Icelandic eruption stopped most of the air traffic in Europe for 6 days. Eyjafjallajökull is a mid-sized volcano under a small ice cap, and its eruption that April was not large by any historical standard, but the ice made all the difference. Meltwater flooding into the vent shattered the lava into unusually fine, sharp, glassy particles, and the wind that month blew steadily southeast, straight over the busiest airspace in the world. Fine ash and jet engines are a poor combination, The glass melts in the hot section and sets on the cooler turbine blades, and there was an alarming incident in the 1980s in which a passenger aircraft lost all 4 engines over Indonesia and restarted them only after gliding down into cleaner air. So the airspace closed. Around 100,000 flights were canceled and 10 million passengers were stranded, and for a week the skies over northern Europe were empty and silent in a way that no one alive had experienced. The other legacy was linguistic. Newsreaders across the world spent a fortnight failing to pronounce the mountain's name. Icelanders enjoyed this enormously, and the country's tourist board later ran a cheerful campaign built on the joke. 69. In 1963, a fishing crew off the south coast of Iceland saw smoke on the water and went to investigate a burning boat, and instead found an island being born. The eruption had begun on the seafloor 400 feet down. Within a week, the new cone had broken the surface and was throwing black ash and steam several hundred feet into the air. Within a month, it was half a mile long. The eruption ran on for 3 years and a half, and by the end there was a permanent island of about 1 square mile, capped with hard lava that could resist the winter storms. It was named Surtsey after a fire giant of the old Norse stories, and then the Icelandic government did something quietly wonderful. They closed it. From the beginning, Surtsey has been off-limits to everyone except a small number of scientists, so that the arrival of life could be recorded without interference. Seeds washed ashore. Gulls nested and brought nutrients and more seeds in their droppings. A single bush appeared, then more. Insects blew in, earthworms and spiders followed, then flowering plants, and eventually a small ecosystem. The island is slowly eroding and will likely be a reef in a century or two. Until then, it is the most carefully watched square mile of new ground on the planet. 70. Volcanoes are also occasionally funny, and the historical record does not always cover itself in glory. There was a Victorian gentleman who charged tourists to be carried up Vesuvius in a chair, and a competing funicular railway whose owners commissioned a song to advertise it, which became one of the most famous Italian tunes ever written and is still sung in kitchens across the world by people who have no idea they are singing a railway advertisement. There were the 18th century travelers who dined on the warm rocks of an active flow and cooked eggs in a crack, a habit which persisted for 150 years and produced a great many amused letters home. There was the 1970s proposal to bomb a lava flow to divert it, which was actually attempted more than once in Hawaii, with results best described as inconclusive. And there was the Hawaiian Volcano Observatory's early practice of lowering thermometers into the lava lake on a wire and hauling them out again, which cost them a great many thermometers before somebody invented a better method. The subject attracts a particular kind of person: patient, unbothered by discomfort, willing to walk a very long way to put a thermometer somewhere absurd, and generally cheerful about the whole business. 71. Roughly 1 person in 10 on this planet eats food grown in volcanic soil. The proportion is startling until you list the places: the rice terraces of Java and Bali, the coffee slopes of Colombia, Costa Rica, Guatemala, and Ethiopia, the vineyards and citrus groves of Sicily and Campania, the maize fields of the Mexican highlands, the tea gardens of Kenya and Sumatra, the vegetable country of the Canary Islands, the orchards of the Cascade Valleys, the dairy pastures of the North Island of New Zealand. Those soils are called Andesols, and they make up only about 1% of the world's land surface while feeding a wildly disproportionate share of its people. They hold water like a sponge, they resist compaction, they are loose enough to work with simple tools, and they release minerals steadily for centuries. Farmers knew all of this long before anyone had a word for it. The old advice in volcanic districts was to plant where the ash fell, and the old land prices reflected it. And family holdings on those slopes have been passed down for 20 and 30 generations. If you have had a cup of coffee today, there is a fair chance the plant that grew it had its roots in weathered ash. It is among the quietest connections between the inside of the earth and an ordinary morning. 72. Iceland heats 9 out of 10 of its homes with water that came out of the ground already warm. The country sits on so much heat that geothermal energy is not a novelty there, but the default. Hot water is pumped from deep wells, piped into towns, run through radiators, and then, in the capital, run underneath certain pavements and car parks before it is finally released, so that the snow melts as it lands and the streets stay clear all winter. Around a quarter of the country's electricity comes from geothermal steam as well, with most of the rest from water power, which makes the Icelandic grid one of the cleanest anywhere. The bathing culture that grew out of this is the part visitors notice. Nearly every settlement has a public pool, open all year, heated for nothing, and used in the evenings as the ordinary meeting place of the town. People stand chest deep in hot water in a snowstorm and discuss the weather with great enthusiasm. Other countries do the same where the geology permits. Reykjavik, Rotorua, parts of Tuscany. The hot spring towns of Japan, where the practice is more than 1,000 years old and thoroughly formalized, and Turkey, where the white terraces of Pamukkale have been used for bathing since Roman times. 73. At the bottom of the sea, along the volcanic ridges, there are ecosystems that never use sunlight. Cold water sinks into cracks in the young, hot crust, is heated far past boiling and kept liquid by pressure, dissolves minerals out of the rock, and comes back up as a scalding, mineral-rich jet. When that jet hits the near-freezing water around it, the minerals crash out of solution as black particles, so the plume looks like smoke, and the structures that build up around the vents are called black smokers. They were discovered in 1977, and the discovery upended a basic assumption. Around them live dense communities of tube worms, clams, crabs, and shrimp, thriving miles below any light. The base of the food chain there is bacteria that take their energy from the chemistry of the water, from hydrogen sulfide rather than from sunlight. Everything else grazes on those bacteria or houses them inside its own tissues. The giant tube worms have no mouth and no gut at all, only an organ packed with bacteria that feed them from within, which means that life on this planet has at least 2 independent power supplies, one from the sky and one from the heat of the rock, and a second one would carry on perfectly happily if the sun was switched off tomorrow. 74. A microbe living in a Yellowstone hot spring made modern genetics possible. In 1966, a researcher sampling the hot pools isolated a bacterium that was thriving at about 70 degrees Celsius, well past the point where most living things fall apart. It was given a name meaning heat-loving and deposited in a collection, and there it sat for a while as a curiosity. In the 1980s, biologists working on a technique for copying DNA needed an enzyme that could survive being heated repeatedly. because the copying process requires cycles of heating and cooling. The enzyme from that hot spring bacterium did exactly that. It became the engine of the polymerase chain reaction, which is the method behind genetic fingerprinting, ancestry testing, medical diagnostics, and every genome that has ever been sequenced. The colors of the hot pools come from these organisms. The deep blue center of a spring is sterile, too hot for anything, and blue for the same reason deep water is. Around it, the temperature falls, and rings of different microbial communities live at their preferred temperatures, producing yellow, orange, brown, and green in neat concentric bands. So the postcard photograph of a steaming pool with rainbow edges is in fact a temperature map drawn by living things, and one of those things is in every laboratory in the world. 75. Volcanic islands become laboratories of evolution because they begin with nothing on them. A new island is sterile rock. Everything that lives there had to arrive by air, by water, or by accident, and only a small biased selection of the world's species can manage any of those journeys. Birds and insects and spiders and floating seeds arrive. Large mammals and freshwater fish almost never do. What arrives then has the place to itself and diversifies. In Hawaii, a single ancestral finch produced dozens of species with different beaks for different foods. One founding population of fruit flies produced several hundred species found nowhere else. The island's plants include an entire family of tree-sized daisies. The Galapagos, all volcanic, produced the finches and tortoises that helped an English naturalist assemble his argument. And the tortoises differ from island to island in shell shape according to whether they graze low grass or reach up for cactus. The same story plays out on the Canaries, on Madagascar's volcanic neighbors, on the Mascarenes, on Iceland to a lesser degree. Each one an experiment in what happens when a small random sample of life is handed a clean sheet of rock and left alone for 1,000,000 years. 76. Coral atolls are the tombstones of sunken volcanoes, and a young naturalist worked that out before anyone had drilled to check. The puzzle is why a ring of coral should sit far out in deep ocean with a shallow lagoon inside it and nothing in the center. Coral only grows in warm, shallow, sunlit water, so a ring of it thousands of miles from any land makes no obvious sense. The answer proposed in the 1830s was this. A volcano rises from the seafloor and becomes an island. Coral grows as a fringing reef around its shore. Then the volcano, being heavy and sitting on cooling crust, slowly sinks. The coral keeps growing upward at just the rate needed to stay in the sunlight, so it maintains its position while the island beneath it disappears. Eventually the peak drops below the surface entirely, and only the ring of living coral remains, enclosing a lagoon where the mountain used to be. It was an elegant idea with no direct evidence for over a century. Then, midway through the 20th century, drilling on a Pacific atoll went down more than 4,000 feet through solid coral limestone and struck volcanic basalt at the bottom, exactly as predicted. 77. Roman concrete was made with volcanic ash, and it is standing yet after 2,000 years while modern concrete crumbles in 50. The Romans discovered that if they mixed lime with a particular ash from the district around Naples, they got a mortar that set hard, kept its strength underwater, and improved with age. They called the ash after the town of Pozzuoli, and the word Pozzolana is still used. The dome of the Pantheon in Rome, unreinforced concrete, 142 feet across, has stood since the 2nd century and remains the largest of its kind ever built. Roman harbor walls dropped into the Mediterranean have survived direct wave attack for 2 millennia. Modern analysis has explained why. The volcanic ash reacts slowly with lime and seawater over decades and centuries, growing new interlocking crystals inside the material so cracks are gradually filled and sealed by the concrete itself. Where our concrete is designed to be as strong as possible on the day it sets and then deteriorates, theirs was chemically alive and got tougher. Researchers are now working on modern versions using volcanic material for the same reason, which is a satisfying loop. The best builders of the ancient world used a mountain's leftovers, and we are going back to look at their notes. 78. Obsidian from a single mountain has been found hundreds of miles from where it formed, in settlements thousands of years old. Volcanic glass is a chemical fingerprint. Each source has its own precise mix of trace elements. So a fragment found in a dig can be matched to the specific flow it came from with real confidence. This has given archaeologists one of the cleanest tools they have for tracing ancient trade. The results have been consistently surprising. Glass from a small Aegean island turns up in mainland Greek sites 9,000 years old, meaning people were making open sea crossings well before farming. Glass from the mountains of Anatolia appears across the Near East. In North America, obsidian from Wyoming has been found in burial mounds in Ohio, some 1,500 miles east. None of these communities had wheels or draft animals in most cases. The material moved on foot and by boat, hand to hand, across generations, through networks that nobody at the time could have drawn a map of. That is the strange gift of a volcano to human history. It produced the sharpest material available before metalworking, it stamped each piece with the address of its origin, and it made it possible for us to reconstruct, from a scattering of black flakes, who was talking to whom 8,000 years ago. 79. There is volcanic material in a great deal of ordinary household equipment. The pumice stone at the edge of a bath is the most obvious, and it is exactly what it appears to be, a piece of frozen volcanic froth cut into a convenient block. Ground pumice goes into heavy-duty hand cleaners, into some toothpastes as a mild abrasive, and into the stone washing of denim, where several tons of it are tumbled with the fabric to soften and fade it. Perlite, a volcanic glass that puffs up like popcorn when heated, is the white grit in potting compost that keeps the mixture open and draining. Vermiculite, another heated mineral, does a related job and also insulates lofts. Diatomaceous earth, though not volcanic itself, is often mined from lake beds preserved in volcanic basins, and is used in swimming pool filters and as a gentle insect powder. Basalt fibre is spun and woven into fabric for insulation, and basalt rebar is being trialed in construction because it does not rust. And the black grit on an asphalt roof shingle, the sand in a filter, the aggregate under a motorway, and the gray chips in a garden path are all quite likely to be crushed volcanic rock, because it is hard, cheap, and everywhere. The inside of the earth is present in most buildings, holding up the parts nobody looks at. 80. Some of the most admired wine in the world is grown on ground that is entirely volcanic, and the growers will tell you it tastes of it. On the flanks of Etna, vines grow in black gravel at altitudes where the nights are cold and the days are bright. Some of them on terraces built by hand from lava blocks, and some on vines more than a century old, which survived the great root pest of the 1800s because it could not thrive in that loose mineral ground. On Santorini, the vines are trained into low woven baskets that sit on the ash, coiled to protect the fruit from the wind and to catch the night moisture, a method used nowhere else and unchanged for centuries. On Lanzarote, where the ground is bare black lapilli, each vine sits in its own scooped hollow with a low semicircular wall of stones on the windward side. Seen from above, the vineyard is a field of hundreds of dark craters, each with a single green plant at the bottom, and it is the strangest agricultural landscape on earth. None of these places would be farmed at all if the soil were ordinary. The volcano provides the drainage, the minerals, and the heat retention, and in exchange it takes a village every century or two, and the vines are replanted, and the terraces are rebuilt. 80, and the light in the room is exactly as low as it needs to be. We have reached the point in the evening where most people listening have already gone, and that is a good thing. And the rest of this is for whoever is still here on the edge of it. 20 facts remain. They are the gentlest of the 100, so there is nothing ahead that will pull you back up. We will drift away from this planet for a while and visit some other worlds that do the same thing in their own fashion, one of them made of sulfur, one of them spraying ice, and one of them carrying a mountain the size of a country because nothing there ever moved the crust along. Then we will come quietly home and finish with the people who spend their working lives listening to mountains, and with the reason any of it matters at all. Before that, let everything soften once more. Let the breath find its own slow pace without being counted or corrected. Let your face be completely idle. Let the last of the day's small unfinished business drain away down through your shoulders and your arms and out through your fingers, because none of it can be attended to at this hour, and all of it will still be available in the morning, should you want it. If your mind has wandered off somewhere during the last few facts and come back, that is not a lapse. That is what a mind does when it is beginning to let go, and it is precisely what we are here for. Picture the island one more time. The long, slow breathing of the water on the rocks, the soft orange coming and going behind the hill, the warm ground under your palm, and the enormous unhurried patience underneath that going down and down, mile after mile, to a place no one has ever been and no one ever will. Nothing there is in any rush at all. Neither are we. 81. The tallest volcano we know of is on Mars, and it is so wide that standing on it you could not tell. Olympus Mons rises about 16 miles above the surrounding plain, which is roughly 2.5 times the height of Everest above sea level. And it is around 370 miles across at the base, about the size of the state of Arizona. Its slopes average a very gentle 5 degrees, so an explorer walking across it would experience an unremarkable upward stroll with the horizon always close by. The summit caldera alone is over 50 miles wide and deep enough to swallow a mountain range. It grew so large for 2 reasons. Mars has weaker gravity, so a pile of rock can stand taller before it slumps. And Mars, so far as we can tell, has never had moving plates, so the crust stayed fixed over one hot spot for perhaps 2 billion years and built the same volcano over and over rather than making a chain of islands. That is the difference plate tectonics makes. Earth spreads its volcanic energy along seams and drags the crust past the hot spots, so no single peak gets more than a few million years of supply. Mars kept the tap in one place and got a mountain the size of a small country. 82. Venus may be the most volcanic body in the solar neighborhood, and it has repaved itself. Radar mapping of the planet, done from orbit because the atmosphere is permanently and completely opaque, revealed a surface with over 1,000 volcanic structures and enormous plains of solidified lava. Strangely, there are very few impact craters, and the ones present are evenly scattered. That combination is telling. A surface builds up craters over time, so a lightly cratered surface must be young. The best interpretation is that Venus resurfaced itself, either in one enormous global episode a few 100 million years ago or through steady volcanic renewal, and that its entire visible face is therefore recent. There are features found nowhere else. Broad, flat domes with steep sides, nicknamed pancake domes, apparently made by very thick lava spreading slowly under crushing atmospheric pressure. Great circular coronae, hundreds of miles across, thought to form where a plume pushed the crust up and it then sagged back. And in 2023, researchers re-examining radar images from the early 1990s found a vent that had visibly changed shape between two passes 8 months apart, which is the strongest evidence yet that the planet is still active right now. 83. The most volcanically active place in our neighborhood is a moon of Jupiter smaller than the Earth's own. Io has more than 400 active volcanoes. Some of its plumes rise 200 miles above the surface, high enough to be seen in silhouette against the black of space from a passing spacecraft, and its surface is a startling patchwork of yellow, orange, red, and white sulfur compounds with almost no impact craters, because it is completely resurfaced every few million years. The heat does not come from radioactivity or leftover formation warmth. It comes from being squeezed. Io orbits close to an enormous planet and is pulled into a slightly stretched orbit by its neighboring moons, so the tides raised in its solid body rise and fall by as much as 300 feet twice every orbit. All that flexing generates friction, and the friction melts the interior. It is the principle of bending a paperclip back and forth until the bend gets warm, applied to an entire world. The first photographs came back in 1979, and the plume that appeared on the limb of the moon was spotted by a navigation engineer checking a star field, who noticed a smudge where no smudge should be. Active volcanism beyond Earth had been predicted a few days earlier in a paper that had barely finished being printed. 84. Some worlds erupt ice instead of rock, and their volcanoes are freezing. At the outer edges of the solar system, water ice behaves as rock does here. It is the hard structural material, and when it melts, the resulting liquid is buoyant relative to the solid. And it rises. That is cryovolcanism. Enceladus, a small bright moon of Saturn only 300 miles across, does it spectacularly. Great jets of water vapor and ice crystals spray from cracks near its south pole, feeding one of Saturn's rings and rising hundreds of miles into space. A spacecraft flew directly through those plumes and tasted them, finding salt, silica, and simple organic molecules, which together suggest a warm, salty ocean beneath the ice in contact with rock. Triton, a moon of Neptune, showed dark plumes of nitrogen when a probe passed in 1989. Pluto has vast, smooth areas that appear to have been resurfaced, and two enormous mounds with hollows at the top that may be ice volcanoes of a kind we have no other example of. So the basic behavior, hot inside pushing out through a cold shell, turns out not to belong to fire at all. It belongs to any world with a warm interior and a lid, and the lid can be granite or it can be ice. 85. The dark patches that make the face on the moon are ancient seas of lava. Early astronomers, looking through the first telescopes, took them for oceans and named them accordingly. The Sea of Tranquility, the Sea of Serenity, the Ocean of Storms. They are flat, dark, and smooth, and they are frozen basalt flows that flooded the great impact basins between about 3.5 and 3 billion years ago. The moon is small, so it cooled quickly and its volcanic period is long over, but for a stretch of several 100 million years, it was thoroughly active. And the material that filled those basins came up through cracks in exactly the manner it does here. The samples brought back in the 1970s confirmed it directly. Lunar basalt is chemically similar to the basalt of the ocean floor, drier and with a few notable differences, but recognizably the same substance from the same process. So the pattern you can see tonight, the rabbit or the man or whichever figure your grandmother pointed out, is a map of lava flows 3 billion years old, still perfectly preserved because there is no weather up there to wear them away. It is the oldest visible landscape any of us will ever look at, and it is visible from a bedroom window. 86. In 2022, an underwater volcano in the Pacific produced a plume that reached higher than any eruption ever recorded. Hunga Tonga sits between the islands of Tonga, its summit shallow beneath the sea. On the 15th of January, it erupted with an efficiency that astonished everyone, because the water above it was at exactly the depth that turns an eruption into a bomb, deep enough to add pressure and confinement, shallow enough not to smother it. The column reached about 35 miles up through the stratosphere and into the mesosphere, which no observed eruption had done before. The pressure wave traveled around the world several times and was recorded on barometers everywhere, including on ordinary home weather stations, and its passing was noticed by amateurs on every continent. It also injected an extraordinary amount of water vapor into the stratosphere, enough to increase the total up there by several percent, which is a genuinely unusual climate influence and is still being studied. And it did something charming. Because it was so well observed by satellites and because home instruments caught the wave, thousands of ordinary people around the world found themselves holding a personal recording of the same event within a day and shared the little pressure blips online. A volcano in the South Pacific rang the whole atmosphere like a bell, and half the planet heard the note on their own equipment. 87. There are more than 100,000 undersea mountains, and almost all of them are volcanoes, and most have never been visited. A seamount is defined as a rise of more than about 3,000 feet from the seafloor that does not reach the surface. Sonar surveys and satellite measurements of the sea surface, which bulges very slightly over the extra gravity of a hidden mountain, suggest the total number is somewhere above 100,000 and possibly far higher. They matter out of all proportion to their fame. A seamount interrupts deep currents and forces water upward, bringing nutrients from below into the sunlit layer, and the result is an island of abundance in an otherwise empty ocean. Corals grow on the slopes. Fish gather. Whales, sharks, turtles, and seabirds navigate between them, and a great many migratory species time their journeys around them. Some of them are ancient and worn flat on top, planed off by waves when they briefly stood as islands, and then carried down as the crust cooled and sank. Those flat-topped ones have their own name, Giots, and finding one is a reliable sign of a mountain that once had a beach. Charts of the ocean floor still carry Great Blank regions, and new seamounts are found on nearly every survey. 88. New islands appear from time to time, and most of them do not last. Off the coast of Japan there is a small volcanic island called Nishinoshima, which was, until recently, a modest rock. In 2013, a vent opened beside it and built a new cone which grew, joined the old island, and kept expanding, until the original was entirely buried and the island was more than 10 times its previous size. In the Red Sea, 2 new islands appeared in 2011 and 2013. In Tonga, several have come and gone. Off Iceland, small cones appeared alongside Surtsey and were gone within a year or two. Whether a new island survives comes down to what it is made of. If the eruption produces only loose ash and cinders, the sea takes it apart in a season or two. If lava flows late in the eruption and armors the surface with hard rock, the island can last centuries. Governments occasionally take an interest because a permanent island extends a country's territorial waters by a considerable area. And there have been polite international disputes about ephemeral rocks in the past. The sea, in the end, keeps its own accounts. It has been given a great many islands, and it has quietly reclaimed most of them. 89. Black sand beaches are made in an instant, in the middle of an argument between lava and the ocean. When a molten flow reaches the sea, the water chills the outside of it so violently that the rock shatters into fragments, and the steam explosions blast that material apart further. The fragments are dark basalt glass, hard and heavy, and the waves carry them along the shore and pile them into a beach. Because the process is quick, a black sand beach can be created in a single eruption, in a matter of weeks. And because the supply stops when the eruption stops, the same beach can be worn away entirely over the following decades with no new material to replace it. Several famous ones in Hawaii have appeared and vanished within living memory. They are noticeably warmer underfoot than pale beaches, since dark sand absorbs sunlight rather than reflecting it, and on a bright afternoon they can be too hot to cross barefoot. Iceland has spectacular ones, long and dark under gray skies with white surf, backed by columns of basalt. Sicily, the Canaries, Tahiti, Hawaii, Bali, and the Aleutians all have their own. Standing on one, you were standing on rock that was liquid at the moment of its manufacture, cooled in seconds, and rounded by nothing more than a few years of patient water. 90. There is a beach in Hawaii where the sand is green, and there are only a handful like it in the world. The green comes from olivine, a mineral that crystallizes early and at high temperature in basalt magma, and which is dense and reasonably durable. When the surrounding rock erodes away, the olivine crystals survive longer than the softer material around them, and if the local conditions concentrate them, the result is a beach of olive-colored grains. Papakalea, at the southern tip of the Big Island, sits in the eroded remains of a cinder cone that was unusually rich in the mineral. The sand there is a soft, army green, coarse and glittering, held in a curved bay beneath crumbling cliffs, and reaching it requires a walk of a few miles across open ground with no shade, which keeps the crowds modest. Olivine is common in the mantle, which is largely made of it, so in a sense a green sand beach is a rare direct look at the material of the Earth's interior, sorted and cleaned and delivered to a shoreline by the sea. Gem-quality olivine has its own name, peridot, and it serves as the birthstone of August. Some of the finest specimens ever found came out of a volcanic vent in the Red Sea, mined on a small island since the time of the pharaohs. 91. A modern volcano observatory listens to its mountain with 4 senses at once, and none of them is sight. The first is hearing. Seismometers buried around the flanks pick up the tiny fractures made by moving magma, and the number, depth, and location of those small shocks can be plotted over days to show where the material is going. The second is touch. Tilt meters and precise satellite positioning stations measure the shape of the ground to within a fraction of an inch. A mountain filling with magma swells, and a mountain that has emptied sags, and both are detectable long before anything is visible. The third is smell. Instruments sample the gases coming from vents and fumaroles, and the ratio between sulfur dioxide and carbon dioxide is especially informative, because the two dissolve out of the melt at different depths. A rising proportion of sulfur suggests magma has come close to the surface. The fourth is temperature, watched from orbit. Satellites carrying infrared sensors pass over every volcano on Earth regularly and record hotspots, so a new thermal anomaly in an unpopulated region can be flagged automatically. Put together, these give a picture that no single measurement could. And the great majority of the time, that picture says the same thing it said yesterday, which is precisely what it is there to confirm. 92. Before a volcano erupts, it breathes in, and the whole mountain gets slightly bigger. The swelling is called inflation, and it happens because magma arriving from below occupies space and has to push the surrounding rock aside. On a large volcano, the effect might be a few inches spread over an area of several miles, which no eye could ever notice. Satellite radar catches it. By comparing radar images of the same ground taken weeks apart, the technique measures changes in distance to a precision of millimeters and displays the result as a set of colored rings like a contour map centered on the point that moved. A textbook inflating volcano produces a neat bullseye. The method now runs more or less automatically over every volcano on the planet, and it has found swelling at mountains nobody was watching, including several previously considered inactive. The reverse also shows. After an eruption, the ground subsides as the pressure is released, and the same rings appear with the colors reversed. There is something oddly companionable about it. Twice a month, a spacecraft passes silently overhead and checks whether a mountain in an empty part of the world has changed shape since it last looked, and then files the answer, and almost always the answer is no. 93. The world's first permanent volcano observatory was set up in Hawaii in 1912 by a man who was told the idea was impractical. He was a geologist who had become convinced that volcanoes should be watched continuously rather than visited after the fact, in the same manner that weather is watched. He raised money privately, largely from businessmen in Honolulu, built a small stone building on the rim of Kilauea's caldera, and began keeping a daily record of the lava lake below. That record has never stopped. It ranks as one of the longest continuous scientific observations of any natural feature anywhere, and its early volumes contain hand-drawn sketches of the lake's surface, notes on its level, and cheerfully opinionated remarks about visitors. He also worked out, by simple persistent measurement, that the level of the lava lake rose and fell in step with the swelling of the ground, which is the founding observation of everything in the previous two facts. There are now more than 80 observatories in dozens of countries, tied together by an international network sharing data automatically. The building on the crater rim eventually had to be moved twice because the crater kept changing shape underneath it, which the founder would have regarded as an entirely reasonable outcome. 94. Most volcanoes give weeks of warning, and the difficulty is rarely the science. The hard part is what to do with a warning that is honest. A scientist can say that unrest is increasing and that an eruption is likely within weeks, but not exactly when or exactly how large. An official has to decide whether to move 10,000 people out of their homes on that basis, knowing that a false alarm costs money, disrupts lives, and spends credibility that may be needed later. Everyone in the field is aware of both kinds of failure. There have been evacuations that proved unnecessary and were criticized, and there have been warnings that were not acted on with consequences that shaped the profession. What has been learned is that the communication matters as much as the measurement. The most successful cases involve scientists who spent months before the crisis talking to local leaders, mapping hazards in plain language, and building enough trust that when the recommendation came, it was believed. There is a term for it now, and it appears in the training of every volcanologist. The instrument networks are the easy part. The lasting work is done in village halls with a map on the wall and a lot of patient answering of questions. 95. In 1973, the people of a small Icelandic island stopped a lava flow with garden hoses and fire pumps, and it worked. A fissure opened without warning on the edge of the town of Jaime, and the fishing fleet in the harbor evacuated the entire population of about 5,000 overnight, in good order, in the dark. Then, over the following months, the flow advanced steadily toward the harbor mouth, which was the reason the town existed at all. Somebody suggested cooling the front of the flow with seawater to make it stiffen and stall. The idea was mocked, then tried on a small scale, then scaled up enormously with dredging pumps, miles of pipe, and a crew working shifts around the clock. Something like 8 million tons of seawater were sprayed onto the advancing lava over 5 months. It slowed, it thickened, it stopped, and it stopped in a place that left the harbor not merely intact but better sheltered than before, with a new arm of rock shielding the entrance. Most of the residents came back. The town was dug out of several feet of ash. The new hill beside it stayed warm for a decade and was used to heat houses, and the whole episode remains the only clear case of people successfully arguing with a volcano and winning. 96. About 1 person in every 8 lives close enough to an active volcano to be affected if it erupted. That is somewhere near 800 million people in more than 80 countries, and the number rises every decade, because populations grow fastest in exactly the fertile tropical highlands where the volcanoes are. Hazard maps exist for most of these regions now, drawn from the geological record of what each mountain has done before. Old flows and ash layers can be dated and traced, so a map can show with reasonable confidence which valleys have carried material in the past and are therefore likely to carry it again. The maps are unpopular in some places, for the plain reason that they affect land value and building permission. And there is a long tradition of communities disagreeing with them politely and continuing to build, none of which is irrational, exactly. The soil is excellent, the family has been there for 400 years, the mountain has done nothing in living memory, and the alternative land is worse. It is the same arithmetic as living on a floodplain or a coast or a fault line, which is to say the same arithmetic that most of humanity has always used, everywhere, 90-7. The air you were breathing came out of volcanoes, and so did the ocean. The early Earth had no atmosphere worth the name. Whatever gas it collected during formation was mostly lost to space and stripped away by the young sun. What replaced it came from inside, released by volcanic outgassing across a few 100 million years. Water vapor, carbon dioxide, nitrogen, sulfur compounds, all of it exhaled from the interior through countless vents. The water vapor condensed as the surface cooled and rain fell, and it went on raining for an extraordinary length of time until the low ground held oceans. Every drop of water in every sea, every river, every cloud, and every living body arrived by that route, with a contribution from comets and asteroids that is still being argued over. The nitrogen stayed, and it is still there, making up 4/5 of every breath. The oxygen came later and by a different road, made by living things once they learned to use sunlight. And it took billions of years to accumulate. But the stage those organisms performed on, the water they lived in, and the nitrogen they built their proteins from, came up through the ground. So the mountain glowing quietly on that island tonight is doing, on a small scale, the thing that made this planet habitable at all. 98. Over very long stretches of time, volcanoes and rain together work as the planet's thermostat. The mechanism is simple and slow. Volcanoes release carbon dioxide, which warms the atmosphere. Warmth and rain speed up the chemical weathering of exposed rock, and weathering consumes carbon dioxide, converting it into dissolved minerals that rivers carry to the sea, where organisms build them into shells that eventually become limestone on the seafloor. That limestone rides the plates down into subduction zones, where it is heated and its carbon comes back up through volcanoes and the cycle closes. The self-correcting part is the temperature dependence. If the world warms, weathering runs faster and pulls carbon down more quickly, which cools things. If the world cools, weathering slows and volcanic carbon accumulates, which warms things. The loop has held the surface temperature within the range that permits liquid water for most of 4 billion years, through an enormous increase in the brightness of the sun. The important qualification is the speed. This thermostat operates over a few 100,000 years. It is a magnificent long-term stabilizer and no help at all on a human timescale, which is worth knowing and not worth lying awake about. 99. Volcanoes are how a planet stays alive, and the ones that stop are the ones that go quiet in every other way too. Compare the neighbors. Mars is about half the diameter of Earth, so it cooled faster and lost its internal heat, and its volcanoes fell silent, and with them went the magnetic field that a churning liquid core generates. Without that field, the solar wind gradually stripped away the atmosphere, and the water went with it, and what is left is a cold, dry, preserved landscape with the tallest mountain in the neighborhood standing on it, doing nothing. Our moon did the same thing earlier and more completely. Earth is large enough to have kept its heat, and that heat drives the moving plates, and the moving plates recycle the crust, bury and return the carbon, build the mountains, refresh the minerals, and keep the whole chemistry of the surface in circulation rather than letting it settle into a final state. Every one of those processes is powered by the same warmth you would feel through your palm on that island rock. A world without volcanoes is not a safer world. It is a finished one. 100. Every stone you have ever held was once, somewhere in its history, part of something molten. That is the last fact, and it is the one worth taking with you into sleep. The pebble on a path, the grit in a shoe, the granite of a doorstep, the sand of a beach, the clay in a cup, the chalk of a cliff, the iron in a railing, and the calcium in your own bones. All of it was assembled from material that was, at some point in the last 4.5 billion years, hot enough to flow. There is no rock on this planet that has not been through the cycle. Melted, cooled, broken down by weather, carried by water, buried, compressed, heated, lifted, melted again. The earth does not throw anything away. It only reshuffles. And it is still doing it, tonight, patiently, under the floor of the sea and under a few dozen mountains, at the same unhurried rate it has kept since before there was anything alive to notice. So, when you rest your hand on a windowsill of stone, or pick up a smooth pebble from a beach and put it in your pocket, you are handling something that has already been to the middle of the world and come back, and is simply resting between journeys, exactly as you are. Let us finish there. Somewhere out on that dark, warm island, the glow is still coming and going against the underside of the cloud. The sea is still moving in and out against the black rocks. The heat is still traveling upward through miles of stone at its own pace, entirely untroubled by what anyone thinks about it. It has been doing that since long before there were eyes to watch it, and it will keep doing it long after tonight. Nothing about it needs you awake. Nothing about it needs you at all, and there is a peculiar comfort in that, on a night when sleep has been difficult. The world is old and warm and busy underneath, and it is managing perfectly well. And if you remember nothing else from this evening, which is entirely permitted and rather the intention, perhaps keep this much. The heat under that island is not an interruption. It is not something going wrong. It is the ordinary condition of a living world, and every gentle thing around you depends on it. The soil that grew your dinner, the water in the glass beside your bed, the nitrogen in the breath you have just taken and the one after that, the steady magnetic field that has kept the atmosphere from being blown away for 4,000 million years, generated by iron turning slowly far beneath every road you have ever driven on. None of it was arranged for us. It simply happened at a temperature and a pace that suited it over a span so long that our whole history sits inside the last thin layer of ash on a very tall pile. And the work goes on tonight. While whole cities sleep, a fissure somewhere in the north is throwing a curtain of light against a low cloud, and a gray pillow of lava is swelling on a ridge 2 miles below the surface of an ocean nobody is looking at, and a seismometer bolted to a rock in Alaska is drawing a very small line on a screen in an empty room. Nobody has to attend to any of it. That is rather the loveliest part. There is a phrase that turns up in the field notebooks of people who spend their working lives on these mountains, written after a long climb and a longer wait when nothing much has happened. Quiet today. 2 words, over and over, year after year, in 100 notebooks in a dozen languages. Because quiet is what almost every day is, and quiet is what they are hoping to write. Let that be the last thought. Quiet today. Warm underneath. Nothing required of you. Are you still awake? If you are, there is another long, quiet video waiting for you on the screen, and it will begin the moment this one ends, so you need not reach for anything or open your eyes. If you enjoyed this, a like helps more than you would think. And subscribing means the next one finds you on its own. And do leave your town and your local time down in the comments so that someone lying awake on the other side of the world can scroll down and feel a little less alone at 3 in the morning. Let your shoulders come down one last inch. Let your hands go heavy. Let your breathing slow into the same unhurried rhythm as that sea against those black rocks. In and out. In and out. Close your eyes now. Good night and sweet dreams.